we're back at it again after 3 years of not having Devcon, so we are all pretty happy to have you here. My name is Franziska, and I'm going to be your host for this room for today. So welcome and come through if you're standing by the entrance, because we have a couple of very, very nice talks lined up for this afternoon. Mostly covering developer infrastructure, but also later in the day talking about ZPKs, Zero Knowledge Proof, ZKPs. So yeah, there's a lot of cool talks in store, but since we are already running a little bit late with our first talk, I'm not going to use too much time talking about what we have in store, but dive right in and announce our first speaker, which is Piper. Yeah, a long-time core contributor and core developer to the Ethereum protocol. Today he will talk about the Portal network, which is all about lightweight access to the Ethereum protocol. He will explain what this all is about. There has been development going on for, I guess, 5 years already. So yeah, learn what the Portal network is about, how it works, and why it matters for Ethereum. Without further ado, please give a warm welcome to Piper.
Thank you. All right, you guys can hear me. I can see my slides. Good to see all of you today. I'm Piper, as she said, and I'm here to talk to you guys about the Portal network. So let's just get right into it. I work for the Ethereum Foundation. I already got introduced. So this is about actually finally bringing lightweight, decentralized access to the protocol. And yes, this has been kind of a long-term project to get us to where we're at. Here we go. So let's dive into kind of at this high level what the Portal network is. For me, it's a giant white whale that I've been hunting for a long time and hopefully doesn't eat me in the end. But the Portal network is 5 new decentralized special purpose storage networks that serve all of the data that is necessary for interacting with the Ethereum protocol. And this has been a long road to get to here. We spent time way back trying to build lightweight clients on the existing networks. And where we ended up was that the existing networks don't give us what we need to actually deliver lightweight protocol access. And thus, we have these 5 special purpose storage networks that we are building out to serve this data and to essentially realize this, this dream of lightweight access to the protocol. The project has kind of these high-level design goals that kind of informed what we needed to build and how it needed to get built. And one of the main things is that the Portal network is really user-focused. All of the clients that you hear about today, Geth, Besu, Lighthouse, all of that stuff, right? It's infrastructure for the protocol, and those clients are built with the protocol in mind. And the user-facing stuff, right, the JSON RPC API, they're not the lowest priority, but at the end of the day, those clients serve the protocol and not the users. One way to look at this is that if you want to interact with the Ethereum protocol today, you have 2 choices, right? It's the upper right or lower left-hand corner of this graph. You can run a full node. They're very heavy, and they're also awesomely decentralized. There's a number of choices for what to run, but in general, when we're talking execution layer, you're talking about very heavy pieces of software. We'll get into the details of this in a minute. On the other end of the spectrum, you've got lightweight but centralized options like Alchemy or Infura, things like that. Somebody at the last conference told me that I was a boomer for calling it Infura. I thought that was awesome. So anyways, you've got these lightweight options, but they're also centralized, and they can do things like correlating your IP address with the transactions you send, or selling your data and things like that, right? There are 2 options at the far opposite ends of the spectrum, and we want to build this thing in the upper left-hand corner, this kind of adorable pink smart car, that is both lightweight and decentralized, which supposedly we care about. This brings us to this lightweight concept. Like I said, Ethereum clients are heavy, and we need a network that allows lightweight devices to participate. Ethereum clients are heavy today because they have to do a lot of things EVM execution is CPU intensive. Running the transaction pool is CPU intensive. And there's gigabytes upon gigabytes of history and state data and things like that that they need to do. This means that running a traditional Ethereum client is an inherently heavy thing, and you generally can't do it on things like Raspberry Pis or phones. Over here on the left, we've got this nice little strong guy who can hold it all up. That's your traditional execution layer client. Our goal is building out a network that lets you spread things out, that takes all of the load for all of this data and distributes it around all of the participants of the network in a nice kind of even way. The other thing that we focus on is kind of removing some of these height restrictions. And by height restrictions, I mean essentially hardware restrictions that keep you from joining the network. This is one of the things that blocked us from building a lightweight client years ago, was that you've got these sort of you must be this tall to ride things. You are not allowed as a participant in the Dev P2P network, that's the network that supports execution layer clients, you can't be part of this unless you have all of the state and all of the history and enough processing power to process every block and enough processing power to run the transaction mempool, right? If you aren't tall enough, you're not allowed into that network. We focused on a different model. We wanted people to be able, people, clients, computers, whatever. We needed a network that allowed you to show up with whatever you had and to contribute it to the network if you're so willing. The idea is that all of these networks operate on this exact same principle, which is that as a client to the network, you can tune some parameters that dictate how much storage space the network is going to ask of you, that dictate how much processing power the network is going to ask from you. And one of the other major things that we focused on is kind of this UX thing, which means, to me, elimination of sync times. Traditional clients have bad UX in terms of the user-facing stuff, and that's because you either have to, when you start it up, you've got hours or days to wait for it to sync, and if you go offline for some period of time, you often have additional time to catch back up to the tip of the chain. These sync times make UX for kind of end user interactions kind of basically unbearable. This is why almost all of the user land traffic goes through services like Alchemy or Infura. We've designed a system where all that you need to do is have a view of what you think, what you trust as the front of the chain, and from there, all of the data is accessible to you, which means the difference between hours or days of sync time from 0 to being able to actually interact with the network to being able to be interacting with the network in a matter of seconds, or at the worst network conditions, a minute or two, as it has to peer with some other peers in the network. So really focusing on user-facing things like this. The other piece that we needed was something that was scalable. And we're not talking this scaling. This isn't sharding scaling or transactions per second scaling. This is a number of network participants. This is having potentially millions of nodes be part of this network. Some of the past work towards Ethereum light clients is LES. That's the Light Ethereum subprotocol. And this has been around for 5 years, maybe. And it has never really delivered on this goal. And the main reason here is that it exists in this client-server architecture. LES nodes on the network are dependent on full nodes serving them the data. And what happens over time is that a full node who's serving this data ends up getting kind of just assaulted by all of these LES nodes, constantly asking them for information. And they're expensive requests that these nodes are making. And it hasn't turned out super well. LES has not proven, has not delivered a reliable light protocol access. And the main reason is this imbalance between client-server stuff. There's no incentive, there aren't incentives to run LES servers. Running an LES server just costs you something. And so the ones that are out there are being run by the goodness of hobbyists and other people's hearts, or people who misconfigured their client on accident or something, but either way, it costs you something. And the clients in this network are not able to contribute back. As an LES client, you are purely taking from the network, and that is just the way the network is designed. Infura, Alchemy, they're this centralized model, right? Their servers go down, everything stops working. LES is this decentralized model, which we like, but because there aren't enough incentives or anything for people to run LES servers, it hasn't worked out super well. We've moved all the way into this distributed model where we have a homogeneous network where everybody in the network is a client and everybody in the network is a server. One way to think about this is very akin to BitTorrent, where in LES, you have this like kind of degenerative thing where the more nodes you add into the system, they take up a limited amount of capacity, and once you exceed that, it degrades service for everybody. In the Portal network context, we have built these networks around this idea that the more nodes you throw at it, the more powerful it gets. And that's kind of the whole core part of this. All right, let's look at a practical example of what, how you would serve this, essentially a balance inquiry from the Portal network. I'll remind you, we've got a number of different networks here, and the idea is that they're all sort of special purpose, partitioned off from each other. Clients can be part of any number of them that they want. This example is going to touch 3 of our networks. So what we're going to do here, it's a very simple example. We're looking up your Ether balance. So this is our traditional client. You've got databases over here on the right where they're storing information. It's running this JSON RPC server. A request comes in to query my balance. The JSON RPC server is going to do a couple of things here. It's going to reach into an index to figure out what the client thinks the head of the chain is. It's going to look up the header for that header from whatever database it stores headers in. Once it gets that back, it can look at a field inside of that to see the state root, and then it reaches into the state database to actually read your account balance, right? This all happens very quickly under the hood, and the reason that a traditional Ethereum client can do this is because it is maintaining these databases, that it is constantly online, and it is constantly keeping these things populated. The Portal network concept is very similar, right? There's very little, right? This is like, oh God. Nope, wrong direction, too much. So in the Portal network context, when this ETH get balance request comes in, instead of reading from local databases, what a client's going to do is it's going to actually reach out into these networks that it's part of to get the data. We have a network for essentially tracking the head of the chain that provides the beacon light protocol data. Your client's going to reach into there to know what the front of the chain looks like, what the head of the chain is. It's going to use that to pull the header from the history network, which stores all of the historical block bodies, headers, receipts, things like that. And once it has that, it can look up what state root it's supposed to be looking up things under, and it can reach into the state network to grab that state, look up your balance, and return it to you. This is a very simplistic example, but this is very representative of what the majority of requests are going to look like. There will be a little bit of sampling of data from different networks in order to get the information that you need before it's returned to the user. All right, where are we at? Like I said, this has been a long road to get here. We had to build some of the wrong things to figure out what the right thing to build was. And at this stage, we are past the research stage. We are purely in the get it built and get it out the door stage. We have 3 different client implementations. This is fantastic. I'm so happy about this because we wanted to build a protocol, not a singular client. We wanted to build something that had many clients to it, and that would, instead of just one reference implementation. We've got Tren written in Rust by my team at the Ethereum Foundation. We've got Ultralight written in JavaScript by the JavaScript team at the Ethereum Foundation, and we've got Fluffy written by the Nimbus team, run by Status. And here we are. So here's our rough timeline right now. Software estimates are garbage. Imminently, we are right at the edge of getting our first network really fully up and running. That's the history network. In parallel to this, the merge has sort of kicked off us having this beacon light network, and that's sort of like our next major priority. And after that, over the course of 2023, we are going to be getting the remaining networks online. The 0 to 1 is a lot harder than building the subsequent networks that come after that. And we've spent a lot of R&D getting to this stage where we almost have the history network up and running. That is what I've got for you today. If you want to get involved, we are findable on the internet. Like Danny has often said, the doors are all wide open and unlocked. If this is a project you'd like to get involved in, please feel free to reach out to me. And I've got some time for questions, if that's something we can do. I think we've got a guy with a mic walking around.
I have a question related to like the API endpoints which the portal network can serve. Will it be able to serve like debug endpoints that like need like a whole archival storage on nodes?
If I understand correctly, you're asking about the debug-spaced JSON RPC endpoints?
Yeah.
Not initially. All of the data to do things with those will, in theory, be present in the network. But we are really focused on like human-driven wallet interactions. That's kind of like our primary use case that we're focused on delivering. And the debug endpoints just don't play a role in that. And in general are going to involve a much heavier level of requests and like data access than is traditionally involved in kind of standard wallet interactions. So no, the debug namespace endpoints are not officially supported.
Thanks.
Hi, thank you. From the perspective of an application layer client, is the thinking that an application would be like speaking directly to, like an application would want to run one of these light clients itself and speak to that? Or is the thinking that for some reason you would bundle the client itself into the application, or neither of those things? Just trying to grok what the use case is.
I think I understand the question. So there's a lot of ideas on the table, and exactly which ones are going to stick and which ones aren't is, right, we'll find out as time goes on. But the general idea was to build a network where the clients can be lightweight enough that you might have 2 or 3 of them actually running on your machine at any given time, because in theory they're lightweight enough to actually embed. So if you're downloading a desktop wallet and the portal network's up and secure, up and live and production ready, it's entirely likely that it might just bake the client right into the application that you're running, and there might be 2 or 3 others running alongside of it. One of the things that my team's going to be focusing on is sort of like a system-level process that's really easy to download and install, that just runs the thing in the background, which makes it easy for you to do things like connect MetaMask up to it or things like that. So I don't think that there's one model here. I think some applications might embed it. Some might treat it as an external dependency.
Hi. Here.
Yep, there we go.
Yeah, so something that I'm familiar with the LES client that is that when you want to execute for like a smart contract call, you might need to do several round trips, because you are basically, every time that you need to query state, you are going to go to the full node and ask for something, right? And that maybe creates, like, again, several round trips, which increase the latency of like whatever you're trying to do. So is with the portal network, do you kind of have some solution for that, like trying to kind of batch that?
I think the question is, because the requests are going out to the network, there's going to be some inherent latency overheads that come with that?
Not that precisely, but that you're going to do multiple requests. So for example, if you want to do RC20 balance off, you need to download the smart contract, then you need to start executing, and every time you need to access some part of like the state database, you're going to just go again and make a query. And so you are basically doing multiple requests.
Multiple concurrent JSON RPC requests. That's the kind of concept here?
Yeah, I think currently you do them sequentially. And so basically you are increasing the total latency of like balance off. But if you can find a way of like doing that concurrently or batch, that you only do a single request.
I think that's going to be a thing that individual portal clients figure out on their own. There's nothing inherent about the networks that keep you from looking up large swaths of data in parallel at the same time. And anything that can be parallelized at that networking level will definitely benefit total amounts of latency that users experience.
Okay, thank you.
Where do you see zero knowledge being used in an implementation of a light client for the portal network?
Currently, it isn't part of any piece of our roadmap. It's not my expertise. So I don't know, I think, is the concise answer there.
Okay, thank you.
I'll get you next.
Hey, Piper, great talk, man. Just had one quick question. What prevents me from running a light client and making it a freeloader that does no work? How do you prevent against?
We don't. So there's two things that I'll say here. One is that we had to pick some cutoff points for what we were building because this is big. I took a lot of stabs at making lightweight protocol access in smaller ways, and this is what came out of really trying a bunch of things and them not working. So in order to deliver this, we needed to build something that was much bigger than I originally thought we were going to have to build. And in that, we had to kind of cut it off at a point. The thing that we're building is attackable. There is a attack surface that exists, and the general idea here is that those are solvable problems, and we're not going to focus on absolutely trying to make sure that we have them all solved on day zero. The portal network is not core infrastructure, not at the protocol level. The protocol, as we know it, does not depend on the portal network for anything. And so if the portal network falls over, Ethereum does just fine. And initially, it's possible that somebody attacks it. And that probably means we're doing something that's working because it's worth attacking. So that's the one piece, which is that we have built something that we know we are going to have to hone and fine-tune and work on the security part of it.
Thank you.
I held up 2 fingers, and I swear I had a second thing. I
have a second question that might be leading. I'm kind of also curious if I choose to make my light client act maliciously, and you asked me for the ETH balance.
There we go, freeloaders.
I got you, yeah.
The network is designed to, if there are too many freeloaders, it'll degrade performance for everybody. I'm relying on essentially 2 things, which are the laziness of people. So people are inherently lazy, and so going and configuring your client differently than how it ships is something that people often won't do if it's working just fine. And if we ship it with sensible defaults that aren't running your fan speeds at full speed and aren't filling up your hard disk, the chances of you taking the time to go in and tweak those settings are pretty small. And and you can call it altruism or you can call it laziness, but we're fundamentally built on this idea that these small contributions of lots and lots of people add up to a lot, right? BitTorrent works. You can download things pretty fast on it because there's a lot of people doing it, and most of them aren't screwing with their settings too much to just leech from the network. So, can we get the mic over? Sorry. Yes, I'll get you next.
Yeah, just a small question. You mentioned the Beacon light client network as well. So what sort of data are you planning to distribute in the Beacon client network that you talked about?
There's, I believe, 3 data types that we'll be working with. I am going to potentially botch this if I list it off the top of my head. Kim on the Fluffy team is the one kind of leading the R&D or the specification for what that network serves. But it's the light client update objects. And there's 1 or 2 more. But essentially, it's the minimal objects that we need to be able to do the Beacon Light protocol to jump to the head of the Beacon chain. Just bringing a mic. Oh, you have a mic. Sorry. I can't hear you. I'll repeat your question.
I was just wondering, when you're testing on a day-to-day, what user flows are you using for your tests?
Well, so we're designing at the JSON RPC API level. So we're not necessarily building interfaces for people. We're taking the JSON RPC API, which is like the standard API that execution layer clients expose to users, right? This is what Alchemy generally exposes. These are the things that MetaMask is like calling to. And so while we are user-focused, we are building out clients that can serve the JSON RPC API, which is still a low-level thing, right? You're still talking about computers talking to computers. The wallets and things that get built on top of this, that's, I think, the type of user testing you're potentially asking about, and that's kind of like outside of our purview. I guess you could say that the wallets are our primary client and that the users are the wallet's client, if that makes sense. Is that, okay.
Two questions. Are we talking about one-to-one JSON RPC compatibility? And the second question is, what does the roadmap look like for L2s? Because light clients are inherently very useful for cheap operations, and that's kind of where stuff is going. So that's it.
I think you asked whether we're building out a like one-to-one to the JSON RPC API. We are not trying to redefine the JSON RPC API. It is established and has been successful and is generally the backbone of any kind of Ethereum interactions that wallets and things are making. And so we are building off of the existing standard. I don't have an answer for you on the L2 thing. It's an open question. We'll see how it goes. And that is all of my time. Thank you all.
Thank you so much, Piper. And also, thank you for the audience. This was a super nice Q&A session. Keep the questions coming for the next speakers as well. So moving on from the Portal Network to our next talk, I'd like to invite David to the stage. He will talk about debugging the Ethereum merge with parallel universes. And in his talk, he will explore the difficulties of developing stateful systems like a blockchain with high confidence, and will explain how the merge required special testing in order to find the worst possible bugs in these systems beforehand. So please give it up for David. David?
I'm just going to present on. All right. Oh, okay. Excellent. Okay. Can you all hear me? Are we ready to go? Oh, cool. Excellent. Well, welcome. So, if you're in the wrong room, this room is talking about testing the merge with parallel universes. My name is David Searle, and I'm the head of EMEA for a small startup that's been working with the Ethereum Foundation for just over a year now. Who likes bugs? Okay. Okay, well, I brought some bugs along with me today, so you're going to have to be like, who would like a bug? Because I've got some bugs that actually I'd like to give to various members of the audience. Anybody? You'd like one? Okay, here we go. Just have to, are you good at catching? So, little bugs. We've been spending the last year kind of really stress testing. Want a bug? So, you see, this is why you should stay at the front. So, I've got 3 more to go. There we go, see? So, the talk's about testing Ethereum, and it's basically looking at using a pretty sophisticated and unique testing methodology, which is based from a company called Antithesis, which I belong to. The company is involved in using deterministic simulation techniques to allow us to basically explore a whole host of iterations of complex distributed technology that's running in a simulated environment. So let me just get my little clicker. Here we go, let's see if we can do that. I brought a few stars along to the show. Obviously, I've just explained who I am. Little did you know that Dr. Strange and Cher are also going to participate in this presentation. I've got about 25 years worth of experience just in the tech industry. For the last 2 and a bit years now, I've been working for this business, Antithesis, and they've basically made me into somebody that's a bug hunter by trade. I never thought testing could be fun, but there's nothing like hitting a seg fault and actually getting a real kick out of it. And that's what I do on a day-to-day basis. So this is my house in the UK. You can tell from my accent. And as you can see, I've mostly got a few GPUs that I've got to sell. So if you're interested, please let me know. No joke. But the day of the merge came round, and we'd been doing a lot of work with all the various clients, all that hard, arduous testing, making sure that we caught every last bug. What was going to happen? Was it really going to be smooth sailing? I think we saw this morning, which obviously is great news. But I was wondering if we were going to see this. You have to press play on the video. There is sound as well, but I couldn't believe this when I saw this, but this is real.
You gotta put it in the shoe.
Yeah, it's pretty bad, eh? Not my front garden. We don't need it again. So, testing is really important, and this is where we talk about it. But the merge was a significant event. That's why we had so much celebration across the world about kind of what was really going on when the merge took place. So, congratulations to anybody that was involved in the merge. Phenomenal job, and I think we can hold our heads up high there. So, I say testing is hard, and you only got to use Cura to basically ask the question, what makes software testing difficult? It's a bit of a high-level question. Apologies for that. But these two really kind of sort of struck me here. Like the first one, this is something that basically fundamentally this is an impossible requirement because absence of evidence is not the evidence of absence. And so often we run these simulations in parallel universes, hitting a whole host of code, and it's clear, and you're like, well, is that good? Who knows? Like, we can only really understand how much coverage we've got, and it may be good, maybe bad. Who knows? So that's a phenomenal kind of requirement. The second one is then about kind of understanding, like testers have to think about all those possible scenarios where issues may arise and ensure that they are handled by the code, and that's just not. It's just like, how do you approach that with a distributed architecture like we have with Ethereum? We've got a whole host of different clients using different architectures. We've got the execution layer, we've got the consensus layer. It's amazing to see it actually working, but the complexity of that is just phenomenal. If we then look at kind of what Ethereum has done to approach this task, and this is not looking specific at Antithesis, we are a part of the equation, and think very much we're complementary, is that Ethereum is using unit testing, testnets. We've got a host of shadow forks and testnet merges that occurred. There's some technologies that are being used called Hive and Kurtosis that do similar pieces to the equation. We then have Antithesis that is then doing this deterministic piece, which allows us to really get into the detail of all the different iterations that are possible. And then we have a host of different fuzzing technologies that the Ethereum are using to really try and isolate and kind of hammer areas that are of concern. So throughout the entire year, a huge amount of testing is being done, and on top of that, they've also used static analysis to help with doing code audits and making sure that we catch things before the merge was to take place. So I'd step back a little bit in terms of kind of the testing is hard statement. It is a phenomenal kind of obstacle to try and get over. Like how do we find every iteration, and how do we find those hard to reach bugs that may not be common ground, but if they do occur, will be catastrophic. And so if we just look at the right-hand side, this is a representation of a distributed network. So on the right, we're going to call this node. We're going to call this node using Lighthouse and Geth. So Lighthouse and Geth are running on this node. They're running on an operating system, leveraging CPU. We've got a file system. They've got different processes happening. And then inside those processes, we've got different threads being used as well. So just in its own sort of node, there's a lot of complexity about what's going on. And we can test a node. We can test maybe a combination of Lighthouse and Geth working together, making sure that we're kind of pushing the boundaries. But if we then think about how we then have a network, and we have a whole host of different nodes running together, and may have other underlying pieces like databases and other pieces kind of actually on top of that, the complexity of all those different communication channels operating just means that the search space for hidden away little gems, I call them gems, but they're bugs basically, they can hide away for a long time, and you may never find that search. When you're looking at your testing, you may never find that particular condition where the network was slow and there was a bit of thread pausing going on in a certain node, and the number of things that have to happen could have a bug manifest. And so this is really where we step in, because we then have the complete picture, and this is what we build inside our simulation. We have the ability to kind of run the entire collection of consensus clients and execution clients in a simulation, run it, and understand exactly kind of every way in which we can actually kind of see outcomes. That's pretty intense. How do you do that? And fundamentally, how do you do that in a deterministic fashion? If we find a certain situation where Lighthouse crashes, well, can we represent that again? Can we replay it? Can we? It's the first thing you do, right? Can we reproduce it? And often bugs are not reproducible. They often, they might try something different. They might move around. How do we debug this? And this is again where we step in. So what do? We leveraged the ability to auto-generate networks inside this simulation environment and stand up all the containers that were necessary to bring up Ethereum. We then were able to then use network faults and other types of faults to just inject chaos into that running environment. Obviously, it's great to see the software handle that. It's designed to handle these types of things. So, under duress, we see things going wrong. And we basically use fuzzing technology to basically hit the entire system. Not just individual pieces of software, but the entire system is fuzzed. And that allows us to basically kind of deterministically replay the complete orchestration of a situation. Not just one particular application, but we know that in this combination of different clients, under these network conditions, something goes wrong. And so we use strategies inside the system to allow us to seek rare events. And so when I start looking at the numbers and kind of what we've been doing over the last year, we hit a huge amount of code edges, a huge amount. And so how do we find and allow ourselves to seek out those edge cases that, if they do happen, again, can be pretty catastrophic, but get to them and uncover them to help the client teams debug and fix. So we have the ability to have all this wrapped up in a tool set that is available to ourselves, and we share it to the rest of the client teams and EF, and that's been really, really useful. I think if we look at it, we have the individual testing going on, which is fantastic. We continue to promote that and say keep going with that. We have the testnets and shadow forks. Again, I think we can all say that they've been tremendously successful and useful. And then we have our parallel universes. We have the ability to run not just one simulation, but we're running simulations literally every day that are generating and using, exploring the various search spaces that exist across any number of different branches inside the repositories. So what does this mean for us? Well, there's a little help from Dr. Strange here. Hopefully you've seen it, because it's not playing. Here we are.
Strange, we all right?
This is what I look like when I'm doing the work.
Be back here.
Hey, what was that?
Went forward in time to view alternate futures.
to see all the possible outcomes of the coming conflict.
How many did you see?
14,605,000. How many did we win? One.
So for us, winning is finding these edge cases, right? Winning isn't like, oh, all tests passed, yay. We want to find those really intricate kind of combinations and iterations where we've covered 14 million different scenarios, and we've got, maybe not more than one, but we at least have one. We can actually hold a hat on. So that's an example of what we're doing, and we think that kind of represents pretty good sort of analogy. If we move forward, we've seen it again. Here we are. This is kind of what it looks like in our world. We're looking for bugs. This is an example of an output of just one run. So we ran this 13 hours worth of wall clock time, which is, if you look at the wall and there's a clock on it, it will last 13 hours. But it actually allows us to exhaust 536 hours worth of testing. And you can see here, we're talking about an enormous amount of edges being seen here. The branches are kind of how we get decision points. We get like an if-then-else kind of statement inside the code. Very simple example, but just take it. We can basically branch off at that point and exhaust both avenues and actually see what happens in both situations underneath those, under those test conditions. That's an example of a branch, and obviously the code edge, the edges seen is we've got the instrumentation happening, so we can see what kind of functions and pieces of code are actually being executed. Pretty insane. That's one run, and we've got 180,000 edges that we're seeing across the entire network. It's a busy network, and obviously with all the different clients happening, there's a lot going on. So we see ourselves as a complementary piece. We've been looking at this as a great example of a project where we can basically work alongside all the other pieces that the EF are kind of using and the different client teams are using. So we're just another layer in the growing list of strategies being used. And I think that's sort of testament to the approach that EF have used to really hold on to this resilience, making sure that we take advantage of every way we can make sure that nothing untoward happens in the future. More and more upgrades coming, I'm sure. So we've only got 48.4.4 around the corner. I'll say around the corner. We'll see. But it's certainly something to look at in terms of making sure that we're involved at every step of the way. So this is a very simple sort of illustration of what we've been doing. We've been building all of the clients, getting them in place and actually establishing Genesis. So we actually have been using this at a Genesis block and then moving it forward towards the merge in our world. We would have the merge kind of positioned. We obviously start fault injection. We establish a chain and then we start fault injection to get to a point where we've got a whole host of different faults. You can see them here labeled below. So anything from partitioning, that's a great one, obviously, to encourage forking of the chains. We've then also got delays happening, drops of packets. The nodes themselves, we can stop. We put this thing through its paces. We stop things, we pause things, we kill things, we bring them back up. I suppose in some respects it's quite realistic. Things do get rebooted and validators come back up again. We have all that kind of like happening inside the simulation, and then from that we then have any number of threads being paused, released. It's busy. Every type of this sort of configuration of faults that we put into a simulation is again completely deterministic. So if we know that this ended up with a seg fault, we know we can literally put exactly the same into the environment. It's basically creating a pure function of the entire system, and we know we can get the exact same output, which I think is a tremendous piece of technology which we have under the hood. So, what are the numbers like? Well, in 1 year we've conducted 31 years worth of 24/7 non-stop testing. That has processed and explored over 50 million edges of code. Out of that, and you can see there, out of that we've got 45 validated errors, some of which were catered for, but 33 of them were logged bugs that were pretty catastrophic. Things that really would bring either an actual node down, so panics, seg faults. We'd have nil pointer exceptions. We'd have there's one I'm going to bring up in a minute with a little example, but things that you don't want to have like living in your code base, and I think that's we would forward those through to the different client teams, and they've been able to eradicate them, and obviously through the successful merge, it's been great to see our efforts put to the test. So who wants an example? Or I'll give you some. So here's an output of our sort of one of the runs. This would come through from an email. Hopefully you can see it. It's a bit of an eye chart. You've seen the stuff on the right-hand side, but down here you can see a whole host of assertions that we've got running across the entire network. This is actually flagged up by fail. They've got a fail on a seg fault. This is something that is absolutely real. Sig-seg-v. Illegal storage access, attempt to read from nil, ? You get some really interesting ones. You get like, please report this, or please fix this. So this is an example here, and we're like, well, what do we do now? How do we take it to the next step? Because it's great saying, well, you've got a problem. This you can see here is actually for the node that's running Nimbus and Geth. So we know there's an issue there, so okay, fine. Have we got any other occurrences on any other combinations? We do. So okay, that's cool. Well, let's look at an example of an actual kind of log entry that's coming through. So this is a unified log, the serialized activity that's occurring across the entire simulated environment. A bit of a mouthful. So you can see here on the third column, the blue column here, again, this is just showing us all the different combinations. So we've got Prism, Client, Aragon, we've got, there's Nimbus, Nethermind, Nimbus, Besu, all kind of serialized, and you can see that we've got a concept of time running through. So this blown up piece is basically the stack trace of showing us kind of what is happening, and Nimbus is having some issue. It's receiving some JSON, trying to figure out, it's receiving some JSON that's clearly not doing too well for it, so because it basically crashes the entire node. So we go, okay, this is cool. This is why I kind of go, yeah, there's got something of interest here. Another example here. This is just from Prism. Again, I don't love sort of seeing panics, but like it does show that there's something like of value here, that we're really stressing the entire environment. So again, invalid memory address, nil pointer dereference. Okay, cool. What do we do now? Do we just send it to the client team? Well, yeah, you can, and they might go, I wrote that code, I can see what's going on here. Well, she had to do it, didn't she? Yeah, if she could turn back time. Well, the great news about deterministic environments is you can turn back time, right? So we're going to basically jump into the actual environment and actually say, okay, right, when does this manifest? Like, it crashes. Was it a second ago? Was it 5 seconds ago? What happened in the execution paths of all the different operating nodes with all the fault injection going on, or was it? Where do we see this like actual kind of thing manifest? And so we want to look back so many seconds. We may want to turn on packet capture. Packet capture isn't by default just because the amount of data, but it isn't turned on by default. We want to be quite selective about kind of where we see packet capture happening, and then we can look at the data. See, again, we can rerun it. Again, obviously, determinism, you're stressing a little bit of kind of, will it still be deterministic if I suddenly turn on packet capture at a moment in time? We have to look at that. But what we've seen is actually, yeah, you generally, if you've seen something manifest, then we can actively kind of turn on things to help kind of debug and work out what's going on. Got some really interesting stuff coming through next year, which I can't share, but really cool. So this is what we can do today, and this is what we've done with the EF, is basically look at this mountain of data. Like you think about all the stuff that's going on, all the different scenarios, branches, paths of execution that have happened. We have all these available in a big, massive data set. So we can look at this kind of analysis and look at the x-axis, which is your time, versus the probability of the bug occurring on the y-axis. Now, the top right is where the bug is seen. We can then look at the common roots that are happening across all the data and try and then bring it together to see, well, what is happening? Where does the execution occur where suddenly the probability of this actually becoming a bug happen? And lo and behold, we have a huge jump here from literally 0.05% of kind of the kind of bug occurring to over 50%. This jump here in the middle, we can start to go, okay, right, we know how many seconds to go back now. We can actually replay that simulation and turn back time, I won't sing it, and see what's going on there, because otherwise you're looking for a needle in a haystack. Like, how do you do that? And that's really been really valuable in our efforts. So what's next? Well, merge is great, love it. We're doing some post-merge testing on some stable branches, which isn't, we've got things in a fairly good order there. But we know Ethereum's not standing still. We've got, obviously, EIP 4844 just around the corner. I'll say it again. Dank sharding withdrawals, a whole host of new capability, which is, brand new product, brand new code, brand new testing. There's the other pieces in there around, actually, the one that's interesting is using things like malicious clients. What about if I brought up an environment that has a client that is, not doing what it should be doing? Can that cause issues? How does that kind of part of the code for the rest of the network handle that client? And does it operate in the right manner? So other pieces here, you merge code cleanup. There's changes to kind of established pieces of code that are in place now. All those changes introduce problems could go down, could appear downstream. So pretty cool. We're working actively with the clients and open to really kind of broadening that relationship further. So that's the end of that. Q&A. Any questions? I'm not sure if that's 2 minutes of questions or 2 minutes of the end. So, lady in the middle. Do you want a bug? Oh, sorry, late, my man, sorry.
Yeah, you showed us a slide calculating the probability of a bug. I was wondering, how did you calculate the probability of being a bug in time?
Sorry, I couldn't quite hear that. Excuse me, repeat again, please.
Yeah, you showed us a slide with the probability of finding a bug. How did you calculate that probability? Which model you were using, or how complex is, the calculations and that stuff?
That's a good question. So just because of the amount of data we've got available, we know every kind of path execution that's occurring, that the outcome doesn't occur with the bug, and we have then obviously all the different outcomes that do translate to the bug happening. And so the ability to do some simple calculation, we can see that the path that's sort of trodden and worn, if we see this happening, then we can calculate the bug occurring. There are obviously other branches down that well-trodden path where it diverges and goes somewhere else, and the bug doesn't manifest. So that's how we, at every point in that graph, we can calculate if it does contribute or not contribute to the bug. So hopefully that answers your question. After you.
A quick add-on to that question. How do you kind of isolate unique bugs? So how do you know it's like the same bug?
That's a good question. So we see a huge amount of bugs that do manifest and show duplication, like the one you saw with Nimbus and Geth. That we can run that literally day in day out, and it will with the right commit code, which is in history, but we would be able to see that, and we'd see we have counts on that occurrence, so we can see very quickly this isn't just like an edge case that's just happened on one sort of combined client set. It's a problem across the board, and so we have all of that wrapped up into our reporting. Sorry, can you?
Yeah. What do you think about applying formal verification in this huge environment? Is it, do you think, a possibility, or?
I'm actually not the best person to answer that question.
Yeah, okay.
But bring it to us at the end, because I've got some people that can answer that question for you.
Okay, thanks.
Okay.
Questions?
Oh, game over. Well, please reach out to us. Keep the conversation going, and I hope you enjoyed the talk. Okay. I have 2 more. Anybody want?
Thank you, David, and have fun with the bugs, guys. Okay, moving on from testing the merge and debugging the merge to actual testnets, I'd like to introduce the next speaker to the stage, which is Afri. He's the head of protocol engineering at ChainSafe, but not only this, he also is known as the initiator of the Girly Testnet initiative and organizer of ETH Berlin. And in his free time, he's the maintainer of the open source Ethereum and Ruby and Crystal libraries. But today he will talk about testnets and specifically post-merge testnets. The merge has introduced quite a few changes that we are all aware of and how those are affecting the testing infrastructure and which testnets you should be using in future. Afri will tell us everything about it. So please give it up for Afri.
Thank you, Francie. Yeah, let's talk about testnets. Briefly about me, I'm head of protocol at ChainSafe Systems. Thank you, Francie, for the introduction. I'm also one of the co-organizers of ETH Berlin, and I used to work on various EF and ESP grants in the past for both execution layer and consensus layer clients. And among others, as Francie already mentioned, I launched the Girly Testnet with a bunch of cool people that are also sitting here in the room in 2019. So what I'm going to cover today is I want to briefly dive into the Ethereum protocol history prior to the merge, and then specifically take a close look at the implications of the merge on the testnets, and finally give a quick guide to selecting a testnet for your project. So yeah, let's dive right into the protocol history. Everything started with a testnet. Does anyone here know what the meaning of the Ethereum Genesis extra data is? You might know the Bitcoin extra data, Genesis extra data contains a news headline. Does anyone know what the meaning of the Ethereum extra data is? It's actually a block hash from a testnet. Ethereum was publicly fairly launched by announcing a block number on an Olympic testnet. That was 1,028,201. And once this testnet was mined on the once this block was mined on the testnet, this hash could be inserted into the Ethereum Genesis, and the public mining on Ethereum mainnet could start. Olympic was the last pre-release testnet before the Ethereum mainnet was launched, and the first public Ethereum testnet after the launch was Morden. Morden was a proof-of-work testnet using the same ETH algorithm as mainnet, and interestingly, it had a custom starting nonce of 2 to the power of 20 to prevent transaction replays on mainnet. Most of us probably remember the Shanghai attacks during Devcon 2 in 2016. An attacker exploited the long discrete time of the X code size opcode in one of the client implementations, which caused a denial of service of the Ethereum mainnet. Here's a photo of the amazing guest team investigating the issues and coming up with a solution. To address this issue, 2 subsequent hard forks were scheduled for Ethereum. The Tangerine Whistle fork to fix the attack vector, and the Spurious Dragon fork to allow cleaning up the state afterwards. However, this protocol change caused a consensus failure on Morden. This was specifically caused by the different ways how the clients handled this custom starting nonce. And it was then decided it's not a good idea to have a custom protocol on a testnet, and therefore Morden was discontinued and replaced by a new testnet called Rupston. Rupston was the first testnet to launch with chain ID right from Genesis. The chain ID served the purpose of simple replay protection according to EIP 155. So the Rubston testnet was also powered by the ESASH proof of work engine. And we all know proof of work is fairly permissionless. So there's no good incentive to secure a zero-value proof of work testnet. So attackers moved to DOS Rubston, and the testnet was unusable for weeks. In response, Parity launched the Coven proof of authority testnet, and Guess launched the Ringby proof of authority testnet. For the first time, Ethereum had a way to have a more stable testnet environment. However, Coven used the Parity Aura consensus engine, and Ringby used the Guess Click consensus engine, and they were not compatible. Coven was therefore only accessible through the Parity Ethereum stack, whereas Ringby was only accessible by Guess or tooling that relied on the Guess stack. So in 2018, the Gurley initiative attempted to address this by ideating a cross-client proof of authority testnet. In the end, the initiative managed to implement Click in Parity, and subsequently in 2019, the Gurley testnet was launched as a first cross-client proof of authority testnet with validators from both Guess and Parity Ethereum. At the same time, coincidentally, after Devcon in Prague, I believe, the Pantheon client was released. So there was even a third client available for running validators on this testnet. And soon after, also Nethermind joined the validator set. Yeah, later this same year, Parity exits Ethereum and leaving Coven fairly unmaintained, unfortunately. Now, going fast forward in time, just earlier this year, to prepare for the merge, some of the older testnets had to be deprecated. The protocol support team announced the end of life for Rubston and Ringby on the amazing Ethereum Foundation block. They argued the older testnets are harder to maintain due to growing history and state and the growing complexity to run the testnet setup. So in foresight, however, a new testnet was launched, Sepolia. Interestingly, Sepolia, that was just launched not even a year ago, it was launched as a proof of work testnet using the same ESASH algorithm as mainnet back in the day. It was the first time since the Rubston launch in 2017 that we actually launched a new proof of work testnet. The reason was potentially to have another testnet similar to mainnet to allow for, once again, testing the merge under mainnet conditions. Okay, so let's recap the testnets prior to the merge. Morden is fairly dead. It was replaced by Rubston in 2017. Rubston then again was just deprecated a couple of weeks ago. Coven died with Parity leaving Ethereum. Ringby was also deprecated just a couple of months ago, and that leaves us with Gurley and Sepolia as the latest testnets for Ethereum. And now let's just take a look at what it actually means to merge. Yeah, I took a lot of time to build these slides. So in Ethereum, the merge stands for an event where two blockchains are literally glued together. You need a consensus layer beacon chain that takes over finality and fork choice considerations, here shown in blue. And this consensus layer beacon chain replaces the legacy proof of work consensus or other consensus mechanisms on the execution layer here depicted in red. So this slide shows the timeline of the testnet merges. And I added a lot of details here. I'm standing in front of it. I added a lot of details here, but let's revisit this slide in a bit after talking a bit about the implications. So Just to recap, a proof-of-work consensus mechanism is permissionless, as per Nakamoto consensus. So you can just turn on your CPU miner and hope for a block, in theory. On the other hand, a proof of authority is permissioned. Obviously, only authorized accounts may take part in consensus. And then again, proof of stake is fairly permissionless. You have a token and you can stake it to take part in consensus. So what does it mean for Ethereum mainnet? The merge, obviously, moving from proof of work to proof of stake just does not change much in this perspective. It was permissionless before the merge, it is still permissionless after the merge. But how does it look like for the testnets? So Gurley was merged with the Prata beacon chain testnet, and to get access to the consensus on the Gurley testnet prior to the merge was permissioned. So Gurley was running a community-maintained validator set. However, after the merge, it transitioned to a proof-of-stake consensus, interestingly, and suddenly everyone can participate in consensus, given you have access to Gurley Ether. So Gurley used to be permissioned, is now permissionless. But what about Sepolia? As I mentioned, prior to the merge, it was powered by the permissionless eSash proof-of-work algorithm. Here you can see my Sepolia miner. I was happy that I once again can mine a testnet. And yeah, I did not ask for permission. I was just able to mine the blocks. I got a lot of Sepolia Ether. But now there's something unique about the Sepolia beacon chain. Since it was apparent that Gurley will no longer be permissioned, there was actually the quest for having another permissioned testnet to have certain stability guarantees. So it was decided that Sepolia gets a beacon chain with a modified deposit contract that does not accept regular Ether deposits. Instead, it tracks the validator set through an ERC20 token. So in that case, Sepolia is a proof of authority version of the beacon chain, and therefore the access to Sepolia consensus is permissioned. So let's take a look at this overview again. This is a timeline actually on the x-axis. The first testnet to merge was Rupeston. Rupeston was fairly similar to mainnet. It was proof of work. And after the merge, it was proof of stake, right? So permissionless, permissionless. Then Sepolia transitioned with this modified beacon chain. So technically, the consensus algorithm is still proof of stake, but through this permissioned ERC20 token that you require to take part in consensus, I call it, for simplicity, proof of authority here, because the access to this consensus is actually permissioned. And then Gurley merged with Prata and testnet, where exactly the opposite happened. The proof of authority Gurley testnet became a proof of stake Gurley testnet after the merge. And then, yeah, we are here. Eventually, just a couple of weeks ago, the mainnet merge occurred. So yeah, just take a look at the post-merge testnet landscape. I showed you that Rupeston merged. However, it has been deprecated by the Ethereum Foundation's protocol support team. And it leaves us with Gurley and Sepolia as the only long-standing public post-work effect. So if you have an application that you want to deploy on Gurley and you require other applications or interfaces, you might find them on Sepolia, on Gurley, but not on Sepolia, because Sepolia is fairly new and not many applications and libraries are deployed yet. However, it's also longer to sync and more involved to run Gurley infrastructure. So to summarize this, please do use Gurley testnet as it is most similar to the Ethereum mainnet. Gurley is especially interesting for you if you plan to test a beacon chain validator, if you want to test your setup, if you want to test upgrading client versions, if you want to test going through protocol upgrades. Gurley is potentially the best, or if not even the only testnet where you can actually conduct this. Yes, please also do use the Sepolia testnet. Sepolia comes with the best stability guarantees due to the permissioned validator set. Since it's fairly new, it is fastest to sync, and also it has the best long-term guarantees. So I would lean towards recommending to test your applications or even migrate your applications to Sepolia instead of Gurley at this point. Yeah, do not use Rubston, obviously. When I prepared my slides, I realized that we are just in this transition phase where big service providers already start shutting down infrastructure, so you have to expect interruptions and downtime. Don't use Coven for obvious reasons. And yes, also, I would not recommend using Ringb, even though there is some long-term support planned for Ringb for almost another year, but you will potentially not get more protocol upgrades on that network, so I would also not recommend using Ringb in that regard. Yeah, right. There are some caveats, though. As I mentioned, the Gurley testnet has Ether supply issues due to the sheer amount of users trying to test their validator setup. Each validator requires 32 ETH, and if you want to have a more involved setup with, I don't know, 1,000 validators, it quickly becomes a huge burden, huge problem to access these required testnet tokens. This is something we still need to figure out going forward, so if you have an idea, please hit me up. Yeah, and in terms of testnet age, Gurley is also fairly old, so it comes with a fairly big, a rich history and state, and is therefore more difficult to synchronize. Especially now that it's merged with Prata, which also comes with a fairly old beacon chain in combination. And yeah, Sepolia is relatively new, as I mentioned. I wrote down lack of infrastructure. I put it in brackets because it's changing really rapidly right now. I just noticed while preparing my slides that even MetaMask has a Sepolia testnet switch now. So it's happening. I'm really happy that we get all these integrations now. But yeah. Okay, this is my subjective recommendation. If you want to test infrastructure, if you want to test your validators, I would recommend you to run them on Gurley. If you want to test your applications, I would even encourage you to skip Gurley and go straight to run your stack on Sepolia. Okay, this was my talk. Please use Gurley or Sepolia going forward. Find me for some spare Ether cards from East Berlin. They are preloaded with Gurley and Sepolia Ether, so if you want some, I will not throw them into the audience, but just find me after the talk. And yes, since we have a couple of minutes left, please ask questions.
Thanks for the presentation. Is there any tutorial or manual how to be a validator in Sepolia? How to help in infrastructure?
Short answer is you can't. Because, as I mentioned, even though it's proof of stake, you need a special ERC20 token to get access to this validator set, and you would basically have to Google Sepolia GitHub repository, and there is an issue where you can request to be added to this validator set, but in general, not many teams will be accepted, just to keep it really small, the validator set.
Maybe two questions here. One, when EIP 1559 came around, it was very hard to test that in advance because you'd have these proof of authority networks that had no fee market, and then you have these proof of work networks that had like kind of a fee market. You could kind of reason about sort of what that change would do. Sorry, I am leading into a question here. I'm just giving some background. And then Coven, if I seem to remember right, was like Parity Technologies maintained it for the old Open Ethereum parity client, sort of the idea. And I think like now the execution layer is a spec. There's some value behind, testing clients. So I guess just to sum it up to a question, both testing features and execution layer specs, has there any thought then behind testing those kind of things moving forward, spinning up testnets or forks of testnets to do that? So.
I'm sorry, I don't think I got the question. It's also, I don't have the speakers. If you could just try to speak up a bit. Or
so testing specific features of Ethereum forks, like a fee market changes, or testing or validating the execution spec was sort of the goal. Because like you had like, Open Ethereum or Parity and Geth, and whether they synced up or not in terms of whether they're executing, EVM basically correctly was always a question, right? If they ever split. So that's what I'm asking is like where is the testnet infrastructure sort of going in terms of forks and things? They're just going to spin it up whenever or whatever. I don't want to beat this to death.
I hope I understand the question correctly. So I was talking about public testnets today, and public testnets is always the really final stage of testing everything. So if we want to test execution layer changes, consensus layer changes, and whatnot, you usually go from like local simulations to permissioned devnets to through like a lot of hurdles until you actually get to a public testnet. And these testnets, like when I recommend Gurley or Sepolia, they will only get protocol upgrades that have been sufficiently tested before. I don't know if this answers your question. Okay, thanks.
Hi, Afri.
No problem.
That's loud. Do you know why did the mergers happen the way round they did? Wouldn't it have been more logical for Gurley to continue as a proof of authority?
Sorry, I think I have to come down. I just need to be...
I'm just wondering why the mergers happened the way round that they did, as opposed to Gurley continuing as a proof of authority and Sepolia transitioning.
Yeah, thank you. That's a very good question. The reason is that it merged with the Prata testnet, which used to be a consensus layer testnet for a very long time, where many teams already tested running validators for more than a year or 1.5 years. So it was already this proof of stake testnet available, and it was decided not to launch a new beacon chain testnet for Gurley specifically, and just use the existing one. So that's why we had this flip. It was also discussed to maybe have a new deposit contract on Gurley, but in the end they decided it's actually worse for testing the merge to do the big merge. Because Prata was also the only consensus layer testnet that had about approximately the same amount of validators as mainnet. So like long history for them both? Yes. And it was very valuable for
machine image or a new version of the code base. And how often does that happen during the testnet phases?
What's the question? If there's a bug fix on a testnet, how often you have to rebuild your clients?
Yeah, what's the workflow when there is bug fixes applied to the testnets? If you are a validator, there might be a protocol bug. So does the validators get coordinated and they redeploy their nodes multiple times during the testnet rollout?
Yes, this is basically, the answer is yes, but this happens very rarely because most bugs are usually not caught on testnets, but much earlier. I think I'm out of time. Yes, so thank you everyone, and don't forget to run a testnet.
Awesome, thank you, Afri. Yeah, guys, don't forget to collect these sweet Ether cards that Afri has with him, because we all know, or if you guys are developing on a testnet, you know that girly ETH is very scarce. All the faucets are always empty because of some evil bots draining them. So if you want to get your hands on some very sweet girly ETH and Sepolia ETH, come and find him afterwards. I would recommend not in front of the stage, but maybe somewhere else. Yeah, moving on to the next topic, and we are really on time, so that's nice. Please, guys, come in for the next talk. Next up, we will have Khan, who is the main developer of Sourcify at the Ethereum Foundation. And today he will talk about human-friendly contract interactions and explain how source verification projects like Sourcify can help Web3 users take more informed decisions before signing a transaction. So if any of you are guilty of just signing random hex strings transactions, you will now find out what we can do about this as an ecosystem collectively. Please give a warm welcome to Khan.
It's working? All right. So, hello everyone. My name is Khan. I'm working on the Ethereum Foundation, at the Ethereum Foundation on the project Sourcify. And today I will be talking about how we can enable more human-friendly contract interactions using Sourcify verification. So, I'll start with showing you guys something you're all familiar with. I would say if you're a Web3 user for a while, just a normal day in Web3, and I guess this will be like something you see every day, and it's this. So you see every day in Web3, you see things like this, and you basically have no idea. You're not a machine. You don't understand what's going on. You're like trying to make sense of it. Am I doing the right thing? Am I talking to the right contract? Is this doing actually what I want to do? And basically, what you do is telling them to like shut up and take your money. Like you have no idea what's going on, you're just giving out your money. And we say today, a typical Web3 interaction is still a YOLO signing nightmare, what we call YOLO signing. It's just, they give you things to sign and you just like sign on, hope for the best. So at the end of the day, what we want to have is more to the something on the right-hand side, from left-hand side to right-hand side. So I know this has changed actually for many wallets. So many wallets actually started to decode things like MetaMask using Truffle and decoding ABI. But still, we have a long way to go, and we have a lot of things that we can improve the user experience. So what can you do to achieve this? There are two sides of this coin. So there are things you can do as the wallet developer, and there are things you can do as the smart contract developer. So let's dive in what you can do as the smart contract developer. The first thing you can do is using the NatSpec documentation, and as well as doing the source code verification on Sourcify. So what is NatSpec documentation? NatSpec documentation is what is called Ethereum Natural Language Specification Format. It's actually part of the Solidity spec, and probably you have seen this if you have seen a contract before. This is how it looks like. You put the comment, the documentation above the function, and you have the developer documentation, you have the user documentation with the @notice field, and you have the documentation for the parameters. So another nice thing about NatSpec is it has the specification for dynamic expression. So the field you see here, the old owner and new owner parameters in back quotes, these actually can be filled dynamically with the value they are being called. So this replaces the owner, blah, blah, the address gets filled, can get filled, and the new owner can also get filled in the parameters. Okay, so you did your job. You made the user documentation, developer documentation. So where do you find it then? Where can I find it? it is in the Solidity contract metadata. So who actually knows what Solidity contract metadata is? Anyone? Just a few people? Cool. That's why I'm here. So contract metadata is actually something introduced early on in 2016 in the earlier versions, but it was actually not really picked up by the community. It is actually a JSON file generated by the compiler itself, and it contains the metadata. Okay, but what is metadata? It has the ABI, the user doc, dev doc, as well as compilation info and source file info. So the first two fields actually is concerned with how to interact with the contract, so how to interface with the contract. And then the second two is about how to reproduce a contract compilation. So it embeds the information during the contract compilation so that it can be reproduced. The file looks like this. It's a JSON file. It has, as said, it has compiler, language, settings, source file information. And here, for example, in the output, you can see the user doc and dev doc. And if we open that field, those fields again, you have the methods, and with the methods for each method, you have the notice field or the dev doc field if there's a dev doc, and you have the, for example, in this case, the replaces the new owner with the old owner with new owner, the comment we have seen before. You can get the metadata with the metadata flag on the compiler itself. With the frameworks, you can find it inside the build files. So Truffle, for example, puts this inside the build contracts, the contract name JSON. Under that, you can find the metadata fields, and the metadata is there. Hardhat also started to output metadata for inside the build file. Again, you can find the metadata here. Yeah. You can also find the traces of the metadata inside the bytecode. So the bytecode, this is an example contract bytecode, and the bytecode has actually a special field at the end of the bytecode. It is appended by the compiler. Again, a question, who knows what this is? Okay, again, just a few people, and again, that's why I'm here. So this field, the compiler actually takes the IPFS hash of the metadata file, the file we saw, and it encodes the IPFS hash of that file here, alongside some other information. Maybe I'll pull this as well. Alongside some other information. And yeah, you can see how this works in our playground Sourcify dev. We basically show how the encoding is done, what the encoding contains, and we also try to fetch metadata from IPFS. It's already there. So it's a nice tool. There are some example contracts you can click on, or you can just provide us with the contract address, or just paste the contract bytecode, and we will try to visualize how this thing works. All right, let's go down to the second thing, source code verification on Sourcify. But before, what is source code verification? So this is, for all of you know, this is like, you probably have seen this if you have seen a contract before. And you see a green check mark, you're happy, you know the contract, right? Okay, but how does this work? Maybe before that, like it is, the reason why we need source code verification is that the contracts actually live on blockchain as bytecodes. Like they are, we humans write code in human language, but the machines read it in bytes, so the code gets compiled and deployed to the blockchain, and this information is lost in the process. So we need to somehow make sure just a random code you see is actually the code behind the contract. So that's the process of knowing this code is actually the one that is running the contract is source code verification. So how does this work? You have the contracts, Solidity files. In this case, you have a target contract. You also have compilation settings, like the version, the optimizer settings, the other things. And we feed those into a compiler, and we recompile the contract. And remember, this is actually when the second part of the metadata information comes in handy. So we use this compilation info to reproduce the compilation of the contract again. So we feed this to the compiler, and the compiler gives us a bytecode. And we also have the contract that we want to verify. So we get the code of the contract from the blockchain. This will give us a bytecode. Then we'll see if these actually match. And in Sourcify, we also have two types of matches. We have the partial match, when bytecodes match, and we have the full match, when both the bytecode and the metadata field match. So right now, today, when you are verifying on Etherscan or any other verifier, they actually ignore this field. Like, they don't make use of this field. They just trim it out. And actually, there have been cases that this was exploited. So it wasn't a serious thing, but this wasn't really was being done properly. But yeah, with the full match, you have a complete match of the bytecode. And here, the metadata actually acts as a compilation fingerprint. So if you match the metadata as well, it means the compilation is exactly the same as the original, or as when the contract was deployed. And the full matches actually cryptographically guarantee that the whole compilation is exactly the same, including the Solidity files, comments, spaces, variable names, anything. Like, even if you change a space, a variable name, it will break the match. So how does this work? Let's see how this actually works. Again, when you are compiling your contract, the compiler takes the hash of each file, each Solidity file. Then the hashes of these files are actually embedded inside the metadata file, the metadata file that we saw, as well as the other sources, not just one. Then, as said, the compiler takes the IPFS hash of this whole file, and then this IPFS hash is embedded at the end of the bytecode. And then we see if these match. If it's a full match, it's a match, it's a full match, if they match. And let's see what happens when you change something, when you make a slight change a space, change a variable name, any comment. So we have my contract diff this time. So the hash of the file will change. Then the hash inside the metadata will change. And in turn, the hash of the metadata file itself will change. So this field will be different this time. And that means this will not be a full match, but this will be a partial match, assuming you didn't make a change that will change the functionality of the contract, just a comment or variable. OK, but then how to verify? So you can use the Sourcify UI. You can give us the source code and the metadata file. We need the metadata file to be able to verify, either from your computer or Etherscan, remote, GitHub, however you like. Then you give us the contract address, contract chain. We try to verify. You can use the API. We have an API endpoint and several API endpoints as well. You can check them out in docs.sourcify.dev. We have some detailed docs about this. And we also have the tooling. So if you are using Hardhat, there's a Hardhat deploy plugin. And with the plugin, after you deploy the contract, you can just pass the network flag and then say Sourcify and easily verify your contract. We have the Remix plugin. If you are using Remix, you can provide the contract address, the chain, then we will verify. We recently have Foundry support. So using Foundry, you can also easily verify your contracts. And we also have some automatic verification, so what we call monitor. So we have a monitor running that is listening on several chains. We are right now listening to Ethereum mainnet, Testnets, as well as some rollups, as far as I remember. So the monitor, what it does, it catches contract creations. And then when it finds a contract creation, it will fetch the metadata. As you remember, it's like IPFS hash is over there. So it will get the IPFS hash, try to fetch it from IPFS. And also the metadata file has the source hashes, source IPFS hashes. It will try to get the source files from IPFS as well. If it finds them, then it will automatically compile and try to verify the contract. So that means actually the second step here, the source code verification on Sourcify, has become publishing your metadata. So you don't even have to take the extra step and go to Sourcify and verify your contract. If you just publish it and pin it on IPFS, we'll just do it for you. Yeah. So we have this contract repo of all verified contracts. It is served over HTTP and IPFS under repo.sourcify.dev. So we pin the verified contract source files and the metadata so that they will be accessible by decoding the bytecode. So here, remember, there is the IPFS hash here, and anyone, if it's verified on Sourcify, we will be pinning it, and there are other people pinning our repo as well, so they will be accessible by their IPFS hash. And yeah, we also serve the repo under an IPNS name on repo.sourcify.dev, so you can also see the contract repo and see the files, access all of them, download the whole repo if you want. So yeah. Okay, so we have seen what you can do as a smart contract dev. Let's see what you can do as a wallet developer. So maybe a short recap, what we are trying to do again. So we have a contract call. We are talking to a contract, and instead of this byte string, we want to show something more user-friendly. So one thing to do is obviously to decode this call, this byte string call, via the ABI JSON. You can show the function name, the variable names, etc. And then you want to show some human-readable description of what the user is trying to do if you have documented your code well. So what you can do as a wallet developer, you go to Sourcify, you repo.sourcify.dev, you get the chain ID, the contract, and the metadata. No, please don't do that. You don't come to us because it's already on IPFS. And the neat thing is it is content addressed, so you know the file you're getting is actually the right file. So your wallet just gets the bytecode of the contract, decodes the IPFS hash here at the end of the bytecode, fetch the metadata that we pinned it for you, and the metadata file has, as we have seen, the ABI and the documentation. Yeah. This is where the first two fields come in handy, how to interface with the contract, and then decode the ABI and populate the NatSpec comments of the contract. So hopefully at the end of the day, we will have something more on the right rather than something on the left. But Sourcify is actually not the only way for human friendliness. The idea behind Sourcify is to have human-readable descriptions via NatSpec, comments found in the metadata. There are other ways to achieve this as well. So one is, for example, these two EIPs by Richard Moore and Nick Johnson. So the idea there is to have an extra function name, an extra function, a describe function, so to say, that will return the user something human-readable. So it can be anything, any custom string, and the contract will return the string to the user and continue executing the actual function. And here the nice thing is it can decode things like ENS commit that is normally it's an hash commit and it doesn't have a meaning to the user, but you can add actually some more custom strings, custom messages to the user that they can make sense of it. But obviously this costs extra gas. The other one is another IP proposal by Dan Finley. There the idea is to give the user this information at the first point of contact. So say you want to do an exchange for the first time at Uniswap. Uniswap app.uniswap will give you the contract metadata. Your wallet will store it. And then your wallet will have the ABI and the describers so that it can show you something more human-readable. The advantage here is it's backwards compatible. So we don't need to change the contracts. Right now, most of the contracts don't have any documentation or anything, or they are not actually documented with the human friendliness in mind. So this will be backwards compatible, but at the same time, this means it's mutable. So it's like it can be changed. So it's a trade-off, but yeah. And also, there are many ways to do better UX. So we can actually show the users many things. So is it You can decode the contract call. You can warn if the user has never been talked to this contract. Show the user if the contract is verified. Block if it's a scam address. Many things, as well as other types of things such as how many times this contract was interacted with, when was it deployed, because a scam contract would be likely more recent and less interacted with. Is this contract audited, and is it audited by whom? So there are actually many ways we can do better. So as a recap, what is Sourcify? Technically, it is an open source automatic smart contract verification service, our monitor. It's a user interface, server, API, and tooling to verify contracts manually. It's a public decentralized content address storage of verified contracts, our repo. And more generally, we are a base layer and a public good for other tools to build on top of us. And we are an initiative to foster the use of Solidity metadata, NatSpec, and full verification. And as well as we are an ongoing effort to improve smart contracts UX safety and transparency. So thank you for listening. If you're interested, you can find us in Twitter, join our Matrix chats. Our code is also at here, Ethereum/Sourcify. Visit our website. And yeah, I'll be happy to take any other questions if you have. Thank you.
Hello, thanks very much for your talk. I'm wondering how well these solutions can handle translation and internationalizations to provide descriptions in multiple languages.
Yeah, that's also one consideration. There, we have the idea of maybe having a custom NatSpec field for translations, and in that field you can actually link to another translations file. So that would be inside the metadata, for example, the translations file, and that will be another IPFS hash, so that you can fetch it and you can have other languages and translations. There's one over there.
Thanks for your presentation. Awesome. Are you thinking about UX regression testing automation somehow?
Sorry?
Are you thinking about end-to-end regression testing automation with Sourcify? So being able to include the dApps in the whole cycle of testing how things look like what can dApps do to make things easier for end users to understand?
I'm sorry, is it having the Sourcify at the whole development pipeline, you mean? Or I'm not sure if I get the story.
Correct. Currently, in order for a developer to somehow test the end-to-end user experience, it's nearly impossible to include the web app and the wallet interaction and the on-chain interactions.
I'm not sure if I get the question correctly, but we are more like a, so we just say people, here it is, here are the tools, here are the files, just please make use of it. So we don't actively get involved in the UX, contract interactions, or that's not in the complete pipeline, I would say.
Hi. For user protection, am I right in thinking that the reputational and statistical characteristics you mentioned are really important?
Sorry, who's talking?
Right here. Because I'm just thinking, and correct me if I'm wrong, but a malicious deployer could create a malicious contract, describe it in a malicious way with NatSpec, and then take advantage of the user.
Yeah, I mean, obviously, we have the assumption that the contract deployer is benign. It's not malicious. So it's we verify the content of the contract, but there are, as I said, there are other ways to do that. For example, audits, scam lists. So this is another aspect. So we have like this neutral eye to what's inside the contract, and it's up to the community and the other types of methods to actually see it's not a malicious contract.
Cool. Yeah. Hi, thanks for the talk. So question I had was for contract coverage, like what is it, like is it limited to what's verified on Etherscan, or in terms of like ABIs that might not be fully complete, like what does Sourcify fully cover?
What do you mean by cover?
In terms of like contract coverage, like if someone deploys a new contract, it's not verified on Etherscan, then do you guys still provide the human readable aspect, or?
Yes, I mean, Sourcify is a completely different thing than Etherscan. Etherscan is both a verification service and a block explorer, but Sourcify is not a block explorer. We are just a contract verification service, and I would say we have different contract sets than Etherscan. So you can actually import, but it's a different contract set.
So even for like new contracts, you guys instantly get into the pipeline, verify it, and then make it readable?
Yeah, exactly.
Okay, gotcha.
Any contract that is deployed, we can just verify.
Gotcha. Okay.
And
cool.
even also different chains. Like we have I think like 30 something EVM chains right now. Mm-hmm. So you can even verify contracts on other chains. But at the end of the day, actually we have support for different chains, but we actually want everyone at some point to run their own Sourcify for their own chains.
Cool. Okay. Thank you.
Maybe last question.
Is it in the scope of Sourcify to like maintain reputation of the comments, or maybe even validate the comments actually reflect the code?
What documents? Sorry, like sound here is not so good.
Is it in the scope of Sourcify to maintain like a reputation score for the comments, or to validate if the comments reflect the code?
The application commits, you say?
Yeah, the comments.
Comments. I mean, no, we just, as I said, we are a tool to achieve this, and at the end of the day, the developers have to document and comment their code. So they have to keep in mind that this might be a user-facing method and properly document it.
Thanks.
Yeah. I think we're out of time. Just find me after the talk, or also you can, find Sourcify and reach us out there. Thank you.
Hey, thank you so much, Khan. I think we are actually running 10 minutes early, so we are trying to delay that again a little bit so that people who are actually coming for the talk that are coming for are here on time. So first of all, I'm just going to talk a little bit so that we are not running 10 minutes early anymore. And secondly, I see that there are many people in the back. Feel free to also move to the front. There's seating space available here. And to basically bridge between the two talks that we've just had and that we will have next, moving from Solidity metadata and contract verification, we now dance for the future. So, and welcome Daniel to the stage. Big round of applause for him. Please welcome him.
Okay. Is that working? Yeah, sounds like it. Okay, yeah, hi, I'm Daniel. I'm in the compiler team for, over 4 years now. And originally the plan was for this talk to be held by Chris, who couldn't make it to Bogotá, so I have to improvise a bit. I brought a lot of code snippets, which will explain what we have currently in the compiler, currently the state of the language, and where we are headed with it. So let me just dive directly into it. I guess if you are familiar with Solidity, which I hope most of you are, because it was kind of like an implicit requirement for the talk, you probably know immutables by now. It's been around for a while, and it's a very highly appreciated feature from our impression, which, I still will quickly explain how they work. That's the owner variable here looks like a state variable, but it's not a really proper state variable in storage, but a immutable variable which can only be assigned to once in the constructor, and then can use as many times as one wants read-only in the runtime code of the contract, but there the access is very cheap. It doesn't require an S load, but it's basically inlined in the code as if it was a literal. So yeah, you probably know this, and people liked it a lot. And an apparent and a very obvious extension to ask for is, why do we only support that for value types? That's the restriction we had so far, that it's only integers, only addresses, but not arrays of things, for example. So this was, for example, is taken from a GitHub issue that I think OpenZeppelin opened with us to ask for an array of immutables, which would then be initialized by index accessing and otherwise work just as one is used to with immutables. And we're working towards that end, but there are some issues with that. So I mean, we have this assignment here where I randomly assign into elements of this array, and in general, I cannot check whether this is really assigned only once. So, I mean, the question is this still an immutable thing in that sense? Also, if I start having arrays as immutables, I will want to have local references to them, which I could then reassign. So if I keep the name immutable, I just changed what this points to. So this is really, it doesn't look immutable. Immutable doesn't fit this concept anymore properly. So let me explain a bit further how immutables actually work. In the constructor, owner is actually a position in memory. So we store whatever you write to this variable in memory, and then when the actual runtime code of the contract you're about to deploy is copied to memory to be returned by the constructor, we fill in from this memory location into the bytecode the value that is there, which in the end results in the runtime code to actually have it as a literal in the bytecode. So this variable in the constructor actually is a memory variable. In runtime, it's actually something that lives in code. But filling in literal values in so basically the push argument into the bytecode won't work anymore for dynamic types. If we have statically sized arrays, we could still do that, and we probably will for efficiency reasons, but at least for dynamic types, if we go full way, we cannot do that anymore because we don't know the length of the thing, so we can't reserve space in bytecode for that. So instead, we need to rely on code copy. And I already mentioned, we will probably want to pass the immutables around by reference. We will want to slice them, which, if you think about all of that together, makes immutables not an annotation for a state variable anymore, but it will become a proper whole data location. So this will probably look like this in the end. As I said, the variable in the end will live in code. So code and the opcode that will access it is code copy. So code is a natural name for these things. So here I have a data variable, a bytes and dynamic array in code, which I can then, in the constructor, just treat like any old memory variable. Assign to it, modify it freely. You can drop the requirement that it's only written to once in the constructor, because that was always an artificial requirement. So if we actually call it what it is, a code variable that will actually be inserted or used as in the code in the end, we can freely modify it. And then in the runtime code, it basically behaves like a call data reference, a read-only reference, only that it doesn't come from call data, but from code. So I can slice it, have local references to it, and pass it around to functions, all with very little cost. This will be a bit tricky to type check in the end, because in the constructor, it is a memory variable. In the runtime code, it behaves differently. So if the constructor calls functions, we need to type check everything twice. But we have different calls for refactoring the type checker to actually do that as well. So we will do that. And there's still some considerations of gas. It would be very handy if I had a code load opcode similar to a call data opcode to actually read single words from code, but we need to refactor the type checker to have be more flexible. For this, we will need that as well. And maybe we will also have linear types, which is how Rust's borrow checker is constructed. But I will now have some examples with some made-up syntax and some made-up constructs, but I'm going to say this is all early research stage, so we have nothing fixed here yet. I'm just telling you where we're headed and what we want to do in the next however long it will take. So the go-to, down-to-earth example of a use of generics is something like a resizable array, so some container, which, in this case, is just an array that if
you want to append something to it, and the array is already full. You just reallocate with twice the size, copy things over, and yeah, otherwise you can just add the element to the end of the array. And yeah, then one can also define an index access as a user-defined operator, which will then have this work as expected, and yeah, a length field could be added to that, all defined in language, which has the advantage, we had often the request to allow slicing for memory types, which we can't because the representation I'll show here doesn't allow it. Since we expect the size to be at the first memory offset where the memory pointer that is the representation type of this points to is the size, we can't just slice away from the first element. For that to work, memory arrays would have to work similarly to call data types, where you have offset and size on stack. It would be a huge effort for us currently to change the entire compiler to change the representation of memory types. If we had things defined like this, it's minimal changes. I can just say now my memory array is defined as a tuple of stack slots. One of them is pointed to a data area, the other is the size. And yeah, have a similar definition as before, slight changes, but a few source changes in our standard library would then be the same as changing the entire layout of memory types, which would be, yeah, month of work while we maintained everything hard-coded in the compiler. Of course, it has also disadvantages. If we actually keep this extremely generic like that, we will lose semantic information. This will actually make memory optimization harder. Because, yeah, what the compiler sees is just a bunch of stack slots. There's no idea that that's actually memory areas we're talking about that are allocated, may only be allocated temporarily, and stuff like that. So I'm not sure whether we will actually go this far. And if so, we will maybe probably do this in a compiler internal manner where we will still assume certain semantic properties about these functions without supporting similar optimizations as we can do if we know what these things do in random user code. But yeah, why did I say stack slot all the time? That's, yeah, maybe obvious, but just to mention, the stack slot would be the one primitive type, maybe apart from product types, and even the basic integer types, size integer types we have right now can be defined generically just, like the other cases we had. So I mean, this will really reduce the footprint. You can could also then distinguish between types that are checked arithmetic and unchecked arithmetic by having very few functions that are generically written, and yeah. So yeah, but not to give make you expect this to happen too soon. We are still in early design phase for generics. There's a lot of questions. This is a very complex thing to do and a very dangerous thing to do because, yeah, all of this needs to be logically well-defined to not bite you in the back in the end. So, I mean, we will take some time to design this properly, and syntax is also a question. There's very much differing opinions on how the syntax for these kinds of things will end up being. I'm not that concerned by that now. I would first want to get the semantics right, but eventually we also need a good syntax for it. And yeah, what I just said, we need to decide what to do with this trade-off between making this the language really self-defined in the very deepest sense, or to have some fixed functions which are fixed in the compiler, which means we can assume their semantics. Or there are compromises between that, but we'll see. So yeah, to summarize what I was talking about and what I wasn't talking about, and we will still do, hopefully, we will in the future try to allow more pre-computation, either in the constructor by the code data location or in compile time by compile time constant expression evaluation, which is something a lot of people have asked for and which obviously makes it easier to write things in that you don't need, for example, magic constants embedded in a contract or whatever, because you can compute them on the fly without it costing. And yeah, the huge topic for the future will be to make the language extensible and self-defining by means of improving user-defined data types, pushing the standard library, and making a move for generics. What we also, of course, can't just ignore is that we're still wasting a lot of memory. I mean, whoever has used memory in Solidity will know that we basically don't free memory, which for a long time wasn't the main concern, but in the meantime is a very huge pain point in, for cost of contracts. There were several approaches we discussed so far for improving the situation there. A long time we wanted to deal with this on the UL level. It turns out that may not be as simple. So maybe we will move actually to analyzing Solidity, which has the properties right there. We shied away of doing that for Solidity being the more complex thing to analyze, but maybe it's fine. We will see. And yeah, we will also, of course, try to move completely towards VIR code generation, but we have some burdens there to overcome still, like the performance of the optimizer, better tooling support. You still need to define good debugging data for the tooling to consume to actually make the experience as nice as with the legacy code generation. The details there would be that the tooling expects certain patterns to remain in the bytecode in the end, whereas the new optimization pipeline will mess them up by optimizing better, but tooling needs to understand that, and we need to output data for it being able to understand that. But yeah, that's hopefully where we're headed. And yeah, I'll close with that. If you want to give us any feedback, help us with designing generics, or criticize what we are planning and saying we are crazy to do any of that, reach out to us. That's the channels we will reach us at. And yeah, thank you. Okay, that took a bit longer than I'd hoped for, but we have time for a few questions at least. What VIR is, okay. I would have assumed you knew, but let me explain that. It used to be the case that the compiler has two backend paths at the moment. So I mean, it used to be the case that Solidity was directly translated to EVM bytecode, and then the only optimizations that took place were on the bytecode level. For the past years, we have moved away from that and have a different new code generation pipeline that translates Solidity first into UL, into an intermediate language, which preserves some structure and which allows for more complex optimizations, more inlining, more analysis, and then only to translate UL to EVM bytecode as a second step, which can reduce gas costs significantly in some cases. In some cases, it's the same as before, but yeah. And yeah, the new pipeline, the VIR is via the intermediate representation, so compilation via UL. Okay, another question. I'm also not sure whether it's still ahead of time and I can, okay.
Thank you for the talk. You mentioned generics. I'm wondering if you could speak to how you're planning on implementing that, whether you're going through monomorphization, because I worry that the code contract size will balloon if you start, doing the C++ style duplication of implementations, or if there's some, uniform representation you can do a la OCaml or, Java.
I think there's not much you can do, actually. I mean, the generics of C++ are different in the sense that they're analyzed differently, and you only get errors on instantiations, but we will still need to instantiate and generate code for each specific case, but that's not worse than what you get now. What you get now is writing by hand for different types, different functions that would end up separately in bytecode. So, yeah. It's nothing is worse than that. That's duplication in code and in bytecode. If we have generics, we at least only have it in source, only in the bytecode.
Hi Dan. So my question is related to that question regarding generics, but from a different aspect. So type system I understand, but once we get generics into Solidity, wouldn't the developer have to focus on 10 more things instead of focusing on writing business logic?
Good question. I would think that the down-to-earth go-to-smart contract writer will not bother with this. It's mainly something for us for defining a standard library and for people writing libraries to support smart contract developer. So I mean, the language supporting generics and having generic types doesn't force you to use them, and it doesn't mean that anybody has to use them, but it will make the language and the evolution of the language much faster and more streamlined. We can, in the future, ask people if they propose a feature to just implement it in a standard library way and then standardize it in the end if it works out, which will, have all the advantages one can think about that. But for user code, for the end smart contract code, the difference is not that large, probably.
Are you going to implement Lambda functions because it saves a lot of code? Are you going to implement Lambda functions? Just repeat the question.
Definitely eventually, I would say. I'm not sure whether, I mean, getting the basic type system going and all that will already take some time. But yeah, eventually this is, of course, something that will make things easier to read, easier to write, and are beautiful. So, and maybe not, I mean, as long as you don't want these things to capture variables, it's easy. Capturing even maybe something at some point we can also consider, but yeah. Not the first thing we will do, but eventually.
Have you been thinking about integrating on-chain computation and off-chain computation in the one source file? This is, of course, very problematic, but in some moment in future we might need it, not necessarily in Solidity, but maybe you should try to think about that.
Yeah, I mean, on the Solidity level, we don't yet interact that much with off-chain computations, layer 2 stuff or whatever. But yeah, we are aware that we need to interact with that and support that where we can. Sure. Okay, I think.
Okay. I think you mentioned something about the performance of via AR. Did you mean how long it takes to actually use it?
Yeah, I mean the compilation time.
Yeah.
The compilation time is kind of like 10 times or even worse in some complex contracts.
Exactly. Anyone that's used via AR today has experienced that. So how much of an improvement do you think we are going to see?
I mean, so far the VIR compilation pipeline has not been written with any performance considerations in mind at all. We've written it for correctness first, and only now are starting to realize how bad that got and that we need to do something about performance there. So I could imagine that we can get quite a way, but yeah, it's hard to tell before actually doing it.
Regarding generics, how much thought is put into the auditability for external code auditors? Will it improve the story, make it worse, more training, can they forget stuff?
I think it will actually improve things. I mean, we have the standard library definitions of all the built-in functionality, which can be exported, which can be analyzed. I think at the point where we have generics going and a standard library going, we will actually, at some point, not promising that happening soon either, but at some point be able to define the formal semantics for the core language that remains, which can actually help formal verification a lot and things like that. So I think reducing the language core that is built in and hidden in the compiler is actually a good thing for formal verification and auditing. Okay, is that more time for questions? Okay, then we still have some time, if there is any more.
You mentioned that the data location is going to be becoming part of the type instead of being associated with the variable. Does that mean that we are going to be able to start writing things like an in-memory array of storage pointers or a in-storage array of code data pointers? Because those are all well-formed, but something like a storage array of call data pointers makes no sense, right?
Yeah.
So what does the well-formedness look like? How does that sort of, you see that restricting that?
I mean, first part of the question, yes, this is what this means. This is what will be allowed. Second part, of course, there are invalid combinations. There are combinations that don't make sense, which then the type system will reject. Okay. Okay, then thank you again.
Thank you, Daniel, from the Solidity compiler team. We are staying in the space of Solidity and moving a little bit towards upgradability. Next up, I'd like to introduce our next speaker, Alejandro Santander. He is the creator of the Ethernaut CTF game and founder of the Ethernaut DAO. If you are a developer and interested in that stuff, I really highly recommend you checking out this game and also the Ethernaut DAO. They have lots of good Solidity tips and tricks on their Twitter account. And today he will be talking about Alice in Proxyland. He'll walk through the struggle of creating upgradable smart contracts and different proxy architectures. So big round of applause for Alejandro.
Thank you. Thank you very much for coming to the talk. So yeah, I've been a Solidity auditor in Open Zeppelin, then I worked with Aragon for a bit, and now I'm working with Synthetics, mainly addressing the problem of how do you build a super complex smart contract system in a way that you can iterate through it and fix bugs and improve and experiment. And other than that, I consider myself a bit of an educator in the space. It's not that I know a lot of things, I just love to empower other people with knowledge, right? So what we're gonna do today is talk about proxies, and then, like in general, and then we're gonna talk about a pretty sophisticated type of proxy that we're using in Synthetics. So I think that it's critical for everyone to understand how proxies work under the hood. I think that it's not okay for a dev to use proxies and not know how they work. But the good news is it's that they're really easy. Like, in the end, there's like no mystery. It's very easy to demystify it, right? So I insist. Besides the proxy I'm going to show, I think the essence of this talk is to promote the awareness of how proxies work. And if you're going to use one, like, make sure that you understand how they work. So to illustrate this, we're going to play them. Like, we're going to start with a very simple contract and make it upgradable and see what happens. So this is the contract. I don't know if it's a good idea to bring in code to a talk, but I don't know if you can see it, but it's just a contract that sets a value, right? It has a function set value. You can set the value, and it records who set the value. It's message sender, and it emits an event. That's it. So this contract is deployed at the 0x1 address, right? And then after deploying it, Bob calls set value 42, right? Then 42 is set in storage slot 0 because the variable is declared. It's the first variable declared. And 0xBob, which is the address of Bob, gets stored in the second slot, which is slot 1. Okay? That's how Solidity lays out storage automatically when you declare variables in a contract. And an event is emitted from 0x1. Now they decide to make their contract upgradable. All right, how does this work? They decide to deploy a proxy, which is just a contract that has a function. You can tell it what the current implementation is, which is going to be the other contract. And then it has like a magic assembly function, which forwards anything using call to the implementation contract. So this is deployed at 0x2. Then Bob calls set implementation 0x1. And in the proxy storage, slot 0 now holds 0x1 because the address implementation variable is declared in slot. It's the first one declared, so it's saved in slot 0. Then they're now connected. This is the proxy, and this is implementation. And Bob calls value, right? It forwards the call to that implicit getter that Solidity generates. And it returns 2, which is expected, right? Yeah. Now, Bob calls set value 1337. Let's see what happens. It gets forwarded using call to the set value function in the implementation, and it affects the storage of the implementation, not of the proxy. And it stores 1337 in slot 0 and 0x2 in slot 1. That's weird, right? That's message sender. So the problem that we have here is that call makes the execution context to be the implementation, not the proxy. Like the event is emitted from the implementation, which is also not a good thing, right? Because you don't want to have a protocol and tell people like to be changing addresses every time you update the implementation, right? So the problem that we have with this particular proxy that uses call is that the execution context is here, right? And we don't want that. So what is an execution context is when you run code, basically what determines which storage space to use, who message sender is, and where emits come out from, right? There's more to it, but that's like pretty much it. So how can we take the proxy, the execution context to the proxy? We just need to use delegate call. So call runs the code that we're running in the current context, and delegate call runs the code in the context of the caller, right? So here we have a second proxy, right? Which is, the only difference is that it uses delegate call, right? It's deployed at 0x3. It's connected to the implementation, the same one as before. And now when Bob calls set value 1337, it uses delegate call, so the execution context is this, right? We are using the storage space of the proxy, which is good. The event is coming from the proxy, which is good. Now Bob calls value, like the getter, right? The execution context is still that, it's fine. Now, this is going to delegate call to whatever is stored in the implementation. And the implementation is in slot 0, and the value now holds 1337, right? So what are we delegating call to? To some contract at 1337, which there's probably nothing there, right? So we have a storage collision, right? We overwrote the address of the implementation with a number, right? So we basically bricked this proxy, right? So delegate call is awesome, but it is dangerous because you have storage collisions. So to solve this, Bob goes to the next level and destructures the proxy storage. So what is destructuring? It's basically choosing where to store something. That's it. It's not using Solidity's custom slots, but just choosing where you put it. So for Solidity, first variable is at 0, second at 1, etc. And you have infinite slots. Destructuring is just picking a custom slot, right? So we have the third proxy here. It's called unstructured proxy. And the difference is that we are not using Solidity's like regular storage slots. but we are declaring where we store things at slot 1000, right? And using that. The code looks a little bit weirder, but that's it. So we deploy this proxy, 0x4. We connect it to the implementation. Oh, this is important. Can you see the storage? The implementation address is stored at the custom slot of 1000. So that's destructured right now. So now we call set value. It makes a delegate call. The execution context is that. We write the new values, but they don't step over, let's say, the implementation address, right? And the event comes from the proxy, which is fine. So we have a proxy that works, right? And now we can upgrade the implementation because we know that it works. So we have value holder v2. The only difference is that we added a new variable called date, right? Just added it on top. And just whenever someone sets the value, we also record when that happened, right? So now we connect the implementation. We call value, right? It delegate calls. And value is whatever is stored at slot 1, right? According to Solidity storage layout. And at 1, we have 0x pop. So another problem. This is another type of storage collision. We shifted the implementation storage, and we have a collision between versions of the implementation, right? We have incompatible storage layout. So Bob understands that to avoid this, in an implementation, you only append to the storage instead of putting it anywhere, right? So he moves the date variable to the end of the previous storage layout. And that's it. That's a pretty simple fix. That's another rule of using proxies, always append to. And now this value is going to get whatever is stored at slot 0, which is 1337, so it's fine. So we avoided that collision. So storage collisions, it's critical to understand when they occur. And it's basically the two types of collisions that I just showed you. That's it. If you get that, you can pretty much think about any type of collision. Things to consider. The execution context is always the proxy, so everything is stored in the proxy. There's two types of collisions that we just talked about. The first kind can be avoided by unstructuring the storage layout, and the second one can be avoided by just making sure that the updates to the storage layout and implementations is valid. Always append, and something to consider, and this is critical, multiple inheritance flattens your contracts, so you cannot predict the storage layout. So you can add a new inherited contract to your super contract, and it can add 5 new variables in an unpredicted part of the layout. So it becomes hard to detect when you have invalid storage mutations, and you need to use tooling if you use proxies. I see a lot of people using proxies and not using tooling, and it's not a good idea. And even if you detect them, and this is not something that tooling fixes, it can be very hard to avoid the invalid mutation. If you have an inherited contract and it causes this collision, to avoid it, you have to do some weird stuff, right? So why not use that technique of unstructuring on everything, not just the proxy storage, but the implementation storage definitions. So here we have value holder before, the implementation before, and the difference is that it uses the same technique that the proxy used and stores everything at slot 5000, right? Everything else is the same. So we deploy this, we connect it to our proxy, which we're not changing anymore because it works. We call set value, right? It makes a delegate call to the implementation. And we can see that we have the gray storage we're not using anymore. We have the proxy storage namespace, let's say, there, and the new implementation namespace here, and they don't collide, right? So we've unstructured the implementation storage right now. So we're pretty happy with this proxy configuration. The context is kept at the proxy, and collisions are avoided using unstructured storage or storage namespace absolutely everywhere. Tooling should still be used to guarantee that there's no storage collision that you don't notice. But the thing is that this custom or manual use of storage makes storage layouts much easier to control. So now that we understand these basic principles of proxies, let's talk about what a multi-contract system looks like in Solidity. So there's no ideal standard solution for multi-contract systems. People often use registries, which is basically a contract that knows every other contract, right? And whenever a contract A needs to talk to contract B, it needs to go to the registry and ask, hey, I want to talk to B, who's B? Here's B. And then it makes a call to contract B, right? And then B needs, if it's a sensitive operation, needs to say, okay, who's calling me? A, is A from the system? It asks the registry goes yes, and then, okay, then you can perform this. It's complicated, and it gets messy pretty fast. So let's try a pretty crazy solution, which is, we're calling it the router proxy. So we basically have a new contract, which is another contract that has one variable. It's called cooled value. And it's also using this storage namespace system instead of Solidity's own storage layout thingy. But that's it. It just records a variable, right? Gets the store, sets the store's value, and emits an event. So we deploy it at 0x8, and then this is the tricky part. Bear with me with this part. Bob uses tooling to build a router, right? So this is basically a table, right? It has the addresses of the two contracts, value holder and another contract, hard-coded. And its fallback function basically has to do this binary search algorithm to determine which implementation has that function, right? Is it value holder or is it another contract, right? And it just checks the incoming selector and forwards it to the appropriate implementation. And that's it. And then it just makes the regular delegate call proxy forwarding. So this is deployed at 0x9. And then we set the router as the proxy's implementation, right? 0x9 is the new implementation. And now we have this. We have the proxy over here. We have the router over here. And we have the implementations over here, right? So when Bob calls set value 7, I don't think you guys see it, but it's calling set value 7 with the number 7. It makes a delegate call to the router, and then another delegate call to another contract implementation because the router figures out that the function set value is in that contract. Let's keep in mind that the execution context is still the proxy. It doesn't matter how many delegate calls you make. It will always be the entry point. So that works. It sets the The other contract's custom slot was 9,000, so it stores 7 right there. And the event is still emitted from the execution context. So if Bob wants to upgrade the system, all he needs to do, like here we're making like a silly change, right? We're just multiplying the incoming value just by 7. This another contract B2 is deployed at 0x10. A new router is generated by the tooling. It just has, the only difference is up there. In another contract has a new address. Everything else is the same. And Bob sets the implementation of the proxy to that new router. So that's how you upgrade any contract in your system. So what would a more complex system look like? Maybe like this. You have the main proxy, right? You have the different storage namespaces of that proxy. And then you have the router, which you keep changing every time you upgrade the system. And you have the different modules that specify a particular behavior of your system. And then you have this thing, which is really cool because called mixins, because it allows intermodular communication in a way that we're going to see that's really efficient and really easy. So yeah, we don't use any storage other than the execution context storage. Gas efficiency, it's like a concern with this pattern because you're doing 2 delay calls. Keep in mind that transparent proxies, the ones almost everyone uses, cost like 3,000 gas. Universal proxies, about 1,600. And this system uses only 2,600 gas, which is all right. And then intermodular communications. How would a module talk to another module? You could cast your module as the other module and just call its function because every module is the system. But the problem with this is that message sender would be lost because it's a call. You break the delegate call chain, right? So you need to delegate call to the other module, just the same like self-casting mechanism, but with delegate call. It works, but there's something much better, which is mixins, which are pieces of code that know how to interact with another module's storage. They're like delegates for that particular part of the logic, right? And they're not deployed, they're just inherited. It's like module A inherits a bit of the code of module B. And the nice thing is that you can tell the mixin to interact with the other module without even making a call. So communication becomes super cheap. Let's see an example. We have owner storage, which just declares a struct with a single variable, that mechanism to get custom storage slots. Then we have the owner mixin, which knows that storage and only has an only owner modifier, right, that does the typical check, right? And then in owner module, we inherit the mixin, which gives us the only owner modifier access, right? And we have a getter for the owner. And now we have a new version of value holder B5, right, that has a single change, which is we're using the only owner modifier here from another module using the owner mixin. So if you want to use this, you only have to change your code style a little bit. It's kind of weird, but you get used to it fast because it's simple. You just need to use storage namespaces instead of like regular variables. And yeah, you get used to it. Should Solidity do this under the hood? There's a proposal from MaxSam4. So it is something that the Solidity team is considering. This could be a language-supported feature to have like a contract hub. And yeah, why use the router? you don't have contract size limitations anymore because you can just combine, like I think I tested it once with like 800 functions, which is pretty crazy. It's like the router merges all the contracts into a single contract. So then, as we just saw, we have good, easy communications between the modules without having to use a registry or authentication or anything. It's ideal for complex experimental systems. And the other nice thing is that the router is, since the addresses are hard-coded, it's very explicit. So it's good for governance. If you want to make an update to the system, you show your community, like, this is what we're going to change. This is what the configuration of the system will look like. It's not hidden in some dynamic storage somewhere. It's right there. And yeah, that's why we're using it as a core component of Synthetics V3, because it's a complex system that needs to not have all the complications of intermodular communications and all that. And well, if you want to try it out, it's a hard hat plugin. It's Synthetics V3 hard hat router. It generates the router source. It manages storage namespaces for you. It performs validations to ensure that there are no storage collisions, and that's pretty much it. That's what the plugin does. So thank you very much. Thank you. Are there any questions?
Okay. Hi. I just want to know if I'm missing something, but this proxy router could be the same as the multi-faucet proxy, you know, the diamond proxy, but with hard-coded implementations.
Yes, I couldn't hear perfectly, but I think you are asking about the diamond proxy, right?
Yeah, yeah.
Yeah, yeah. This is based on the diamond proxy.
So is the diamond proxy, but without getting the implementation from the storage,
yeah,
but instead hard coding them?
Yeah.
Basically?
Yeah.
Okay.
It's some people are calling the diamond proxy a dynamic router, and this one a static router. And we like this one because for our project, because it saves storage reads, because the values are hard-coded, and it's also more explicit. Like what we don't like about diamonds is that you don't, like if you're a community member or whatever, and you want to know what's the current composition of the system, you need to query it a lot, right? But yeah, it's the same otherwise.
Hi. Just one question. So you only used sort of ints and addresses and stuff. What happens with mappings and arrays in regards to storage collision?
Sorry, can you repeat a bit louder?
So if you have an array,
yeah,
does that affect storage collision?
Well, if you declare your array or any dynamic type inside of those storage namespace structs, then Solidity's like regular storage layout system is used, which uses unstructured storage under the hood. Like if you have a dynamic array, the position of that array, I think it's going to be its slot, say if it's 9003 because it's the third variable in your struct, the hash of that. So it's going to be some other random place. So probabilistically, even though they're in structs, some things are going to be spread out, but the probability of a collision is very low, like insignificant.
So you mentioned a couple times that we should use tooling in order to check for storage collisions. What sort of tooling do you recommend contract developers use?
Sorry, I can't hear really well from here. I'm just going to stand there.
Okay, so in your talk you mentioned a couple times that you should be using tooling in order to detect storage collisions. what sort of tooling should developers use in order to do these checks?
Oh, sort of tools. Okay. Yeah. So if you're using OpenZeppelin's proxies, you should use their tooling. If you're using the router, as you can see, we didn't just offer like a solution to generate the code, but it checks the storage layout of your entire project. So in that case, you could use our code, right? So I would say always use the tooling of whoever is providing you the code, the smart contract code of the proxy.
Were there any attempts to solve this storage collision thing on the EVM or compiler level, like to sandbox each context, for example?
I don't think there's a need to. I mean, the way Solidity like destructures arrays and mappings and all that, it's theoretically impossible to get a collision. So there's no need to sandbox it. The problem with collisions is when people use like a design that's not supported at a language or at a protocol layer like the EVM, right? And they get collisions between two contracts, right? So I'm not aware of any attempt at that level to avoid collisions.
Is it possible to migrate an OpenZeppelin proxy to this one, the router proxy, or would we have to start from scratch?
Code-wise, it's pretty much the same. Like you can use a universal proxy as your entry point, so you could probably just use that. And the migration is the crazy thing about this is that the routing occurs at the implementation, right? So code-wise, you're okay. Then storage-wise, right, you just need to probably choose new namespaces and populate the data, right? Or accept that your modules are going to use existing storage, right? And make sure that new modules declare like a new namespace or something. But yeah, sure, you can do it. Even if Solidity like makes this a language feature, you just stop using generated routers and deploy a Solidity hub, right? So it's completely future-proof, I think.
Hola, Ale. Aquí.
Hey.
Ale, how standardized is proxy? Are you the only ones using it, or is someone else using it in production? That's my first question. And the second question is, do you think it will be useful to have something in the, like a public function in the proxy to share the signatures that are being used? So let's say a user or someone that wants to check what is being used doesn't have to dive into the source code?
Yep. So standards, not many. Right now, if you deploy this, you won't see anything on Etherscan, for example. Etherscan doesn't know how to interpret a proxy that has multiple implementations, which is unfortunate, but we're trying to solve that pretty fast. It shouldn't be hard. And your second question, you would just add a module that adopts ERC 165, is it? That just like replies, it has that function, I don't remember the name of the function, that gives you the entire interface of the whole system. Okay, that's it. Thank you very much.
Thank you so much, Alejandro. All right, moving on. I think this is almost our last, no, it's not our last talk in the developer infrastructure. We are continuing with developer infrastructure. As our next speaker, I would like to introduce yet again another OG. Lefteris is an Ethereum developer since 2014. He contributed to all kinds of different projects, from the Solidity compiler to C++ Ethereum to the DAO and Raiden, and now he is founder of Rodkey, an open source portfolio tracking tool. Today, he will talk about how we can build open source tools that help users understand EVM transactions without the need of being a shadowing supercoder. So, without further ado, welcome, Lefteris.
Thank you. Okay, welcome everybody. All right, that's my slides. Good, cool, magic. So, I'll be talking about basically decoding EVM transactions in an open source, extendable, and modular way. Francis introduced me, but for those of you who do not know who I am, I've been in Ethereum since 2014, worked in C++ client in the Solidity compiler, did DAO stuff, White Hat, and the ETC and DAO wars back then. Then I worked on L2 payments for many years and founded Rodkey. Today, I will be talking about user transactions and how we can start to understand them, like what are they and how can we decode them in a human-readable format. So, everybody has used Ethereum in here, and we have all faced these two big problems. Like, you do not know, when you have a transaction, you do not know how to get it. Like, there is no built-in way to get transaction for an address. You need to utilize some kind of third-party service, and that will never be decentralized. Also, once you have these transactions, you really don't know what I mean. There is a complete lack of a universal tool that will decode a transaction to human-readable format. There is some third-party services, but again, they are centralized, and they tend to be protocol-specific. So, what does a transaction look like? Everybody has opened Etherscan and sees this, hex blob. There is no metadata. There is no human-readable info. That's what every new user to Ethereum is greeted with. There is no way to understand what your transaction, like 3-4 years ago, has done. There are ways. We are no longer in 2014. There are ways to gain insight. So you can see stuff in Etherscan with the graph and other centralized APIs such as Covalent, Moralis, etc. So we have all used Etherscan. What are the ways to decode the transaction with Etherscan is that it looks like this. This is a complicated transaction that does swaps over multiple protocols. It's easy to use. You just type in Etherscan, transaction / the hash, and it gives you useful insight, and it's totally free. Of course, there are cons with Etherscan that's centralized. It's proprietary and closed source. That means that there is no way for me as a developer to see how they do what they do or extend it in any way. They know everything about you. I mean, I know the guys from Etherscan, they are good guys, but you never know who in there could be malicious. They can match IPs to your addresses, know who owns what address and where they are located. And it actually does not decode everything. We've all seen that there are transactions that Etherscan doesn't have insights for, and there are other tools that actually can do this. Then there is the graph. The graph is a way, it's kind of an indexer per protocol. They have subgraphs, and they index the chain for a particular protocol, and then you can query this index and get any insight you want. The pros is that it's very good for single protocol data. So for example, here we have the Aave v2 Ethereum by Messari. This is a subgraph that, say, the Aave guys can run in their interface and query any information they want for their protocol. But it has many, many disadvantages. It needs payment per query. This is their vision, that everybody should be paying for every query. It's built for single protocol data, so the subgraphs, so there is no generic solution. If you have a portfolio tracker or a wallet or something that wants to decode every single transaction, no matter what protocol it is in, subgraphs will not work. You will have to basically query every single subgraph and create a subgraph for everything that is not supported yet. And it does not work with local apps, what I like to call true dApps. So basically, when the company that makes the application hosts the code, they can have an API key and pay for the queries. But when it's a local application, there is no way for this to happen. And there are these other centralized APIs like Covalent, Moralis, and Alchemy. They're easy to use. They have pretty cool APIs which can decode transactions, give you all the transactions, but the same concepts Ethers can apply. Like it's centralized, it knows everything about you, it's proprietary, so you cannot extend it. It's not modular at all. So having seen the ways that we can get insights about data, let's see how we can actually get accurate historical data. And let's go to the original sin of Ethereum. Like, this is absolutely bonkers. If any of you has tried to get the history of transactions for your address, you will find out very easily that there is absolutely no built-in way to do this for Ethereum. There is no RPC method. This is all due to the way that EVM works and how the clients are built. But it is really, like, it's absolutely crazy that there is no way for you as a user to get all of the transactions for your address. Someone that comes as a developer outside from Web3 and comes to Ethereum and sees this, they think that we're just crazy, that this is broken. It's not all gloom and doom, though. There are ways to do this. Etherscan, again, comes to the rescue. They have many APIs, and if you combine 3, I think, so this one for transactions, then there is one for ERC20 transfer and one for NFTs. If you combine all of them, you get a pretty accurate picture of what transactions your address has done. Of course, it has drawbacks, right? It doesn't detect all address appearances. It's rate limited, but you can pay for bigger limits. But rate limiting means that it takes time for your query to actually work. It is centralized, so it can go down, they can cut access to the API, or they can do what I said before, that they can monitor you and map IP to your address. The truly decentralized way to go around this is something by my friend Thomas J. Russ. It's called TrueBlocks. It is really the best and most complete way to get transaction data. TrueBlocks detects all appearances of an address. Really, I have seen demos where TJ basically shows Etherscan and then compares it with TrueBlocks, and you can see that for some addresses, TrueBlocks does indeed detect more appearances than Etherscan. It is decentralized, so it runs on top of your local node, so you do not need to do any other network queries. It's super fast. Like, it's really like milliseconds or seconds, depending on the amount of addresses that you query for. And it's built to share this index with others. Of course, like with everything in software, there is drawbacks. It is hard to set up. So TJ is like, who's a lone wolf since I met him in Shanghai in 2016. Now he has a bit bigger team, but it takes time to build something that's easy to use by others. It does require a local node, so you need to be running an Erigon node, I think. I'm not sure if it works with others. And of course, you require TrueBlocks itself to create the index. So building on this, I would like to present what I try to call the stack of true decentralization, which is something that we should be striving for in crypto. So everybody should try to run their own node, so something like a dApp node or a Raspberry Pi with whatever setup you guys want to have. You should run your own client, right? Like for whatever chain you have, run a client for that chain that you want to use. And TrueBlocks actually works for all chains, all EVM chains. So you can have an indexer like TrueBlocks on top that will index the chain and provide you an answer to the question, how the heck, so what what transactions does my address have? And on top of it all, to come and bind it all, you have the aggregating and decoding level that something like Rodkey, but not like a decoding. So Rodkey right now is an application, but imagine a platform where you can have a generic way to go from transactions to a common readable format for what they do. And it's actually consumable by humans. So going from how we get data to what actually would go into this decoding platform that my talk is about. So once you have all the data, like either from Etherscan or from TrueBlocks, what kind of data is this? If you have tried to play with understanding transaction history of Ethereum, you know that there is 2 ways to get data. It's either a trace, a transaction trace, or transaction receipts. There are 2 kinds of traces. One is the gift style trace, and the other is a parity trace. I'm going to go through them a bit fast, for those of you who do not know what they are. So gift style trace is the tracing that comes with the gift client. When a transaction happens, it touches multiple contracts, right? So you make a transaction to a contract, and this one may make a call to another contract, and so on and so forth. And as they do this, they touch the state of these contracts, and they make some changes. So this is what the trace of a transaction is. And the give style trace is the most complete. It's like super detailed. It has every single step of the execution with the opcode, the program counter, the storage diff, etc. It's super detailed. It's very hard to use because for complicated transactions you have like a huge thing that you don't really know what it does, and it can grow extremely huge, like in the gigabytes for really complicated transactions. Then we have the parity style trace, which comes from the now defunct parity client, but it is used, I think, Erigon for sure, and Nethermind, and maybe Besu, I'm not sure. They have 3 commands. One is a trace, that's pretty cool and useful. It gives you a call stack like this of what did your transaction do, the call trace of the transaction. And this actually does not require an archive node. By the way, the screenshot is from a very nice article by Banteg on traces that came out like 2 months ago, I think. So Google like Banteg and transaction traces, and you will you can read about it in more detail. And the other thing that you can use to understand how a transaction, what has it done, is the parity style trace diff, and this gives you really. Oops, sorry. Let's go back. Yeah, cool. It gives you a state diff. For each account that you touch, it gives you the difference in balance, code, nonce, and storage. The cool thing is here, if you have the API, you can play with it a bit, and you can have readable names for the storage slots and how did they change. So this is a very useful insight on what did the transaction do. And of course, then transaction receipts. We've all seen like how a source code of a contract looks like. They have events. These events are actually contained in something that's called the transaction receipt. So let's say for a token transfer, it's I don't know, like transfer, source, destination, and value or something. Almost everything generates them. It looks like this. It's all hex, but if you have the API of the contract, you can decode this into a human readable format. This is how you gather the data, but gathering this data is actually expensive. It takes time, and exactly because this is expensive in resources, persistence is key. So any kind of platform that you create, and the thing that we have created at Rodkey, needs to have data persistence. You can choose various ways. We've gone with a simple SQLite database for now, but this way, when you have gathered all of the data and you know that they are true and will not change, then you can just take it out of the database and reuse it instead of having to requery again true blocks or Etherscan or make a trace again. So we talked about where you can get data, how to get it, and then I'm going to go to the meat of the presentation, which is the decoders themselves. So we want to get human readable format of the transaction data, yes, of the transaction data. So we have gotten either receipts or traces, and with this amazing Inkscape graphic that I made, guys, I'm really proud of myself for this. We can see that you can check for each receipt, for each log, the address, and then send it, depending on the address, to either the generic ERC20 transfer decoder, if it's a Uniswap swap, to the Uniswap decoder, and so on and so forth, like Aave, etc. And all of this will, at the end, emit a common event format. What's more, some decoders feed data to other decoders, so I have to get used to reusing this. The ERC20 transfers create the ERC20 transfer event, and this gets fed to Uniswap, which translates it into swaps. So yeah, such a decoder platform is made on modularity. This is Rodkey's repo, and this is where we have all the decoders, and it's like a huge list. It doesn't have all of them because they don't fit on the screenshot. But the idea is that it's easy to write, easy to use, and drag and drop. That you just drag, so you drop it in there, and it's caught by the system. And then a new decoder is taking into account whenever we decode the transaction. That's the idea. We're not there yet. We build binaries, and this is not as modular as it should be, but the idea is that it should just big drag and drop. This is how the source code looks like. This is, I think, hop protocol to bridge to another chain. So it's hard to read probably, but the idea is that you get from the ERC20 transfer decoder, you get the ERC20 transfer, and then you see, oh, it's a spend. The counterparty is the F bits of hop, and the asset of F matches and the amount matches. So then we transform it into the common event format for hop and give it a nice readable explanation, which is like bridge the amount of ETH to either your own address or to some other address in the chain, so the name of the chain via hop protocol. I talk a lot about the common event format. It's kind of a POC because we are our only consumer right now. It's changing, so this is how it looks in the code. It has like a sequence index inside the transaction, so where did it happen in the transaction? Timestamp, location. Location is mostly something that we use in Rodkey because we subtract everything into this format, not only Ethereum transactions, but your Kraken trades, your Ethereum staking, everything gets subtracted into this least common denominator format. We have the history type, history event type, and history event subtype. So this is what defines the meat of how you define an event, the asset, and the balance change. And then some extra stuff like the location label is, along with the counterparty, is if I send it from me to someone or if I got from someone else. And some extra data, like if it's a CDP for Maker, we have the CDP ID here, etc. As I said, everything is broken down into this thing. Like a swap is 3 of these events. So it's amount out, amount in, and fee out. Or it can be 2 if there is no fee. We are working on this. It's not final, but this is like the idea. This is how a front end can consume and show this code. This should be read, unfortunately, because I didn't take a nice screenshot from the bottom to the top. So I claim my Badger airdrop. So it has 2 events, the gas fee that's burned and the airdrop claiming, then approval to 1-inch V2 and the gas fee for this, and then the swap for in 1-inch for basically immediately dumping the tokens. This is the same thing that you saw in the previous screenshot, basically, these events. Each one of them is one line here. So this is how they are consumed in Rodkey itself, which is a portfolio tracking application. I would like to actually also talk a little bit about the abstraction layer of the vision of Rodkey, which is like, if you take this a step further and not just focus on just EVM code, but anything, like any event, you can get into like an open source middleware that offers an abstraction layer for everything, accounts, balances, P&L, over multiple protocols and jurisdictions. So this is kind of the vision that we would like at some point to go with Rodkey. So we went from a portfolio tracking app to a common EVM decoder, and now more towards a middleware that would offer an abstraction for everything in accounting for crypto. Why? Right? Like people would ask, what the heck? Why would you need this? Because everybody is reinventing the wheel. There is, again, as I said, different protocols, different exchanges, chains, jurisdictions. It's impossible to keep up. I have spoken with people in both small startups and big names in the field for portfolio tracking and crypto accounting. Everybody is saying that this is just too much to keep up. Maintaining just one module is a full-time job. So I believe that there is a solution to this problem. So the problem of everybody reinventing the wheel has a solution that we can have an open source platform or middleware, if you want, maintained by a core team, but with contributors from the entire industry and used by multiple projects. And for the problem of different protocols and jurisdictions and being it impossible for a single organization to keep up, I would like to propose a solution that we can have people incentivized from each chain and protocol with appropriate know-how to come and implement modules in this platform. Again, my amazing Inkscape skills. Imagine a middleware where you have like someone who wants to use to do portfolio trading and accounting, has the core uses Bitcoin and Ethereum, plugs in the Yen module, the Aave module. He also wants to do accounting, plugs in the accounting module, and because he's in Germany, he plugs in the German accounting with FIFO, multiple depot, and LIFO accounting methods. And imagine this middleware basically being used by many people in the field, and in the end, just everything plugging into this. Because it's better to use a common open source middleware rather than every single application reinventing the wheel. Any such platform would have like some super basic requirements. It needs to be open source. Like everybody tries to reinvent the wheel in a proprietary closed source way. This is just absolutely idiotic. It needs to have a modular architecture so that, as we saw before, like be pluggable, have pluggable modules. You're in a different country than Germany, you can just plug the, I don't know, Netherlands accounting module. You don't use Ethereum, you use Kusama, you do the substrate module, and you can do all the Polkadot, Kusama, etc. It needs to have, this is a hard requirement to achieve, but it needs to be multilingual. It needs to have multilingual bindings. Because we at Rodkey are a Python house. We know how to use other languages, but most of our code is in Python. Such a middleware should not limit the user to, so we cannot ask the entire industry to switch to Python if they are to use such a thing. The platform should be built in a multilingual way. And as for incentivization, the creators and maintainers of modules should be incentivized to actually contribute to this platform. If it becomes an open source standard, then everybody should be like, oh, wait, I mean, we made this new platform. We need to write a Rodkey module for it also, because otherwise it's just like nobody will use it. And the core team that builds and maintains it also needs to be incentivized in some way in order to be able to keep building. The ways that this can be is through support to the various teams or through SLAs for software level agreements for companies that may not want to have open source code, so you can have dual licensing. So it's a bit funny. I wanted to show. I saw the timeline thing, and I was in the template that they gave us, and I thought, hey, why not put a timeline? So how the heck did we get here? 2017, I just needed to do my taxes in crypto, and I was like, okay, I'm not gonna. What is the way to do this? There was Bitcoin.tax. There was nothing else back then. I'm not gonna use a centralized service. I just don't trust them. So I just made some Python CLI scripts. It worked. I've not been sued by the German government yet, so it worked, I don't know. And later built a UI around them. In 2020, we made it into a company. We were a team of 2 people, and maybe we had 200 users, 300, and maybe 10 paid. So last year, the app had grown. We hired 1 more developer, and we were 2,000 users and 200 paying users. In the beginning of this year, there is many people who use Rodkey right now. Some like it, some complain they always want more and more, but it is at a level that many people can use it. We are a team of 7 now, 6,000, around 6,000 users. It's hard to know because it's an open source app and we don't have analytics. And 550 paying users. We came all this way without anything, like it was just completely bootstrapped. And from basically your donations through Gitcoin and from integrations with other companies, like Optimism gave us a grant lately, before that there were Kusama, and so on and so forth. So for getting this POC that I described here to the full Rodkey vision, we would need to go further from here and try to grow and potentially get some funding, because with the current team that we have, it's well impossible to actually build this vision. The POC cannot grow to a level of something that can be used by the entire industry with just 6 people, 6 developers. This is just impossible. So with this, I'm coming to the closing notes. So if you like the stuff that you had, like open source, local first, a modular thing that can be used by everybody in the industry, then please talk to me or check out yeah, this thing again. Check out Rodkey.com jobs. We have some open positions. We came here thanks to you. Like, seriously, it's a bootstrap project, and we would not be here without Gitcoin donations and without our premium users. So keep supporting us. You can donate in Gitcoin grants or in buy premium subscription and unlock all of the features of Rodkey. And you can join our community in Twitter or Discord, like that's where all the support is. It would be pretty cool for you to, if you can join the chat and join our community. And if you're interested in helping us grow, in realizing this vision that I try to present here, then talk to me either like any day in the conference or write an email to lefteris@rodkey.com. Yes, with that, that's all. Thank you very much. Any questions? That guy there has a question. I say a question.
Good afternoon. You mentioned the graph and true blocks, and one thing that I don't entirely understand about these two tools to query historical data is that they use a client node. And this node basically is in charge of storing data in a SQL database, right? So isn't this like a centralized way of saving data? Is this when IPFS comes into play? And if that's the case, can you explain how IPFS and a SQL database work together to solve this?
I'm sorry, I really cannot hear you. I heard the graph, and that's all I heard. Like.
Okay, like you mentioned the graph and true blocks.
Yes.
One thing that I don't understand about these two tools is to query historical data is that they use a client node, and this node is basically in charge of storing this data in an SQL database. Isn't this a centralized way of saving data? Is this when IPFS comes into play? And if that's the case, can you explain how IPFS and an SQL database work together to solve this?
No, IPFS doesn't come anywhere in there. Like the graph is, and TrueBlocks completely different things. So the graph is, it creates an index on top of your already existing node data. And TrueBlocks does the same. But TrueBlocks does it in a generic way for all of your transactions, while the graph has specialized subgraphs written by developers of a particular protocol that basically write an indexer just for this protocol. And this lives on top of your node data. It is decentralized. Like the graph, by design, is also decentralized. TrueBlocks is itself also decentralized. It creates this index, and this index is shared, I think it's pinned in IPFS and shared with others who use TrueBlocks. I'm not totally sure on the details of sharing of TrueBlocks, because I'm not a developer, but I think that this is how they do it. As for the graph, they have a decentralized network.
Hey Lefteris, great talk. And here, straight.
Oh, hey,
hello.
I know you.
Hey, Puise. Great talk. So if I'm understanding this right, the idea is if we build this out and get it out there, then like we could get around using services like Tenderly and just basically run Tenderly at home for transaction tracing and simulations and all that.
Yeah, I view it more from a historical perspective, and Tenderly is a current emulator, but yeah, I suppose that you could also do the same. Correct me if I'm wrong, Tenderly is proprietary, right?
Yeah.
Yes. Yeah, I think that they work with traces. They're pretty good, but yeah, proprietary. With such a design, yes, I believe that we could yeah, use this as an alternative. Here? Here?
Hola, awesome presentation, great work. From the developer perspective on a Solidity developer, I think it will be very useful for example, I write a smart contract and I write the decoder. Let's say I write the decoder and I host it on IPFS. have you thought about that, like how we can have like a standardized, I don't know, let's say variable where we define the URI or hash where we set our decoder and you guys can use it? Because you have a list of decoders on GitHub, right?
Yeah, I mean, this is just a different medium of delivering the decoder. But yes, the idea is exactly what you described. So I'm not going to write every decoder. My team is not going to write every decoder. That's impossible. Yeah. But the idea is exactly that you, when you write your smart contract for a protocol, then you say, OK, I'm also going to write a decoder for this. And then somehow it should be delivered to this middleware. Yes, it can be through a link. It can. This is just a POC of what we have right now, the drag and drop in a folder in GitHub.
I think it does add a lot of value if you can also validate the decoder. Because if I do it, I can write a malicious decoder, but we will need like a validation system. And this is a place where I think you can add a lot of value.
OK, yeah, that's good feedback. I got it. Thank you, guys.
Awesome. Thank you so much, Lefteris. That was a really exciting outlook and vision, and of course, yay for open source. From one developer legend to the next, I am very excited to announce our upcoming speaker. It's Richard, who's the author of Ethers and the co-author of Firefly. And today he will walk us through what's new in version 6 of Ethers. So please give a warm welcome to Richard.
I'll talk to you afterwards. Oh. Let's push buttons and see what happens. Thank you, thank you. Hello, buenos dias, everyone. How's Devcon going? Yeah, OK. So for those, let's jump in. I think my slides explain most things. I'm still pushing. Haha. There we go. So my name is Richard Moore. I go by RickMoo online. And so I write an Ethereum library called Ethers.js. So what is Ethers? It aims to be a complete, compact, and friendly Ethereum library that developers can use. But also, part of user-friendliness is safety. Like, don't let the developer do things that like bites in the ass without realizing it. So one of the cool things is the default provider. I don't know where I should stand. So the default provider, basically it lets you just connect to Ethereum. Historically, you had to either run a node or you have to like sign up for Infura. You have to do something to start using Ethereum right away. So we've got like a bunch of relationships with these third-party providers, and right off the bat, you can just connect to Ethereum and start doing simple things. It's heavily throttled, but you can at least do something before deciding whether you want to like get your own Infura ID and all that. This is all the old stuff, so I'm just going to go over it quickly. It's written in TypeScript now, very few dependencies, 26,000 and growing test cases. ENS is a first-class citizen. Everything, including all dependencies, are MIT licensed. And there's extensive documentation, and in V6, the documentation is getting much better. And an important thing is to understand, like, I made Ethers because it's something I needed, and it's something that I use a lot. And so, I mean, it's in my best interest to keep it getting better over time and that sort of thing. I think dogfooding is very important to keeping a library good. Otherwise, you get a library that's very good at Hello World, but very difficult at anything more complex. So getting into the new things than V6 that's coming out. There's currently a V6 available, both on NPM and GitHub. It's still very beta, but it's there to try out. So one of the biggest features is modern ES features. Currently, V5, it targets ES3. So if you are trying to run Ethers in IE3 from 2002, it'll probably still work, mostly. But that's no longer a priority. And so the goal is to start adding kind of like new age JavaScript things. Heavily reduces the code size, because rather than having this big class for big numbers, you can actually just use the built-in big numbers that JavaScript now provides you. I mean, you can now use like the == sign, which is super exciting. If you want to use a big number, you just put an n on the end, and that tells JavaScript this number should be treated as a big literal. Don't go doing IEEE 754 truncation to it and that sort of thing. I'm going to try to go through this faster-ish. If I'm talking too fast, let me know. But basically, it'd be nice to get to the end so people who have questions can ask questions. So another really cool feature that modern JS offers is proxies. For those that don't know, proxies basically are an object, and if you call a property on it that doesn't exist, code gets to run first and decide whether or not it should let you think something exists and continue. So this heavily improves how the contract object works. Historically, if you had like a ABI with multiple different signatures for different methods, it really required you to understand all the rules for how formatting works to normalize a signature in order to access it. So now you can do whatever you want. Oh, wrong button. There we go. So like basically you can have all sorts of white space, extra little letters and whatnot in there, and this will all figure it out at runtime and map it back into that and get the right thing for you. Basically, for all those people who've ever had duplicate ABI definition errors and have filed an issue saying how to get rid of them, this is for you. Typed values are another cool thing. So going back to the same situation where you have two different methods, foo and foo, and they take in different things. In v5, there's no way for it to know which one if you pass in two parameters. An address looks very much like a number, a 160-bit number, but it looks like a number. There's no way for ethers to actually know which one you meant to call. And so now you can do, so this would be an error. It doesn't know what this is. This looks like it could be a number. This is a perfectly valid U in256. So now you can force it and tell it that it's a typed object of an address. And then if you do this, it'll automatically know, oh, this is the one you wanted. So again, really cool things we can do. This is sort of related to proxies, but kind of its own thing. Likewise, if you have, if you're doing programmatic things, sometimes you just have a bunch of keyworded objects. And so, for example, you've got transfer from. It's got a from, a to, and a value. So this is how you would do it in v5. You can still do this in v6. This works fine, using positional parameters. For those that are used to Python, they call them positional versus keywords. But now you can also do typed.keywords and pass in a from, a to, and a value. And it knows that those things should get deconstructed into the from, to, and some value. This order doesn't matter either. If you wanted to construct this object from a bunch of other lines of code, reading stuff in, you can just build an object up and add a to if it's not null, and add a this if it's not that. And then it's off to the races. OK, another big thing is things are now classes. OK, I'm down to 19 minutes. So things have class. Basically, oh yes, so I'll dive into this a bit more, because I think this is a really cool feature in general of something we should be doing more in Solidity. This is kind of steering away from Ethers specifically into more Solidity generically. But if you're using v5, a signature is literally just some dumb object. It's not a class. It's just an object with the values r, s, and v, and that's all you get. By making it a class, it can take in anything, whether it's like a raw signature, or whether it's an r, s, and y parity, r, s, and v, r and y parity, and r and y parity, and s. Whatever random combination of things you have, feed it in. It'll figure it out, give you back the signature you want. And then if you do something like update a value, if you said, for example, sig.y parity equals 0, and it used to be 1, it'll also change the v for you. It'll update all the y parity and s. It'll reflect all the changes so that the signature stays consistent, which means, is this the right slide for that? Right. So you can get all the stuff out of it and that sort of thing, but the cool thing I want to show off is, maybe I'll come back to this in a second. That's how things are done today. Maybe I will explain this quickly. So this is how things are basically done today. So basically people that pass in a signature for Solidity, for doing EC recover on, they pass in a bytes, or they deconstruct it themselves. So that'll be the third slide from now. But they'll pass this bytes object in, and then you've got this expensive, weird byte manipulation library. I mean, it's well written. It's by OpenZeppelin, I think. But you're doing a bunch of string manipulation on byte arrays to figure out where the r, s, and v sit. It's also a huge amount of data otherwise. And then this is what your code looks like. The cool thing with these new things are class. You could, for example, in your code, have a signature that has an r, an s, and a v. And then you can just use the sig type from the struct. And this is your EC recover. So historically, you might have also seen a verify that takes in a bytes 32 digest, a bytes 32v, bytes, or sorry, bytes uint8 V, bytes 32R, bytes 32S, and go off the races. But with this, you can kind of pack them all together. This is the same size for the ABI's point of view, and then you just pass in the signature. And because it's a class, when it's starting to build out that encoded piece of information, it knows to take the R and pack it together with the S and pack it together with the V in a nice compact format, and then you're off to the races. So one important thing to note with this in the next slide is this line here, bloop, does not change. And so you can see you're still creating a signature, you're just passing the signature in verbatim, and yeah, basically it's because the ABI is encoding it, it can look at this object and figure out, okay, I need to take, the difference in this case is the R and the Y parity in S. For those that aren't familiar with EIP 2098, basically this allows you, signatures are much bigger than they need to be, so basically you're used to R, S, and V. That V is actually just 1 bit. And thanks to Homestead, every S value in Ethereum is actually always got the top bit set to 0. So we kind of just like slot that in. And now your signatures are 30% smaller. And yeah, again, feel free to ask questions because these are going to be a little complicated. But you need a little bit of more math to help decouple that. I'm going to bug the Solidity guys to see if we can kind of get this built more into Solidity, so you can just pass in the signature directly. But in the meantime, this is still much simpler than the like couple dozen of lines of byte manipulation libraries that's going on if you pass into bytes. So quick comparison. So if you use the raw bytes like most people do today, it's 160 bytes, which is by itself, just for the call data, is 1,444 gas, expensive, da-da-da-da-da. So if you use decompose, that's 96 bytes. But if you use the compact representation, it's 64 bytes. Yeah, I'm not going to go into more than that. That was just a quick thing for people who are looking at the slides afterwards. Transactions are also now an object. So if you decouple a transaction, if you just feed in a bunch of like a raw transaction object or a bunch of stuff, if you start updating the stuff, it updates the other parts of it as well. Yes, basically, when you have just an object and you set some property on it, you're only updating that property. But with this, when you set a property, it sets that property, but also updates all the entangled properties. For example, if you set the gas price, then the serialized version of that transaction should update. And you can just set things. You can set them to anything that's valid. You could, so in this case, I'm using a big int, but you could pass it a string. You could pass in a hex string. You can pass in pretty much anything you want that makes sense for a max fee per gas, and it'll be reflected. 13 minutes bits. So this is just like little odds and ends of like random things. So pausing providers. So for example, a lot of people find that people keep their customers keep their app open in a tab that they're not even looking at anymore, which means that their events are still firing, it's still hitting the Infura, gobbling up all their requests. Well, because there's now these visibility APIs available in browsers, you can tell Ethers, by the way, when I'm not visible anymore, pause the provider. That way, if they go to another page for a week and then they find that tab that's left around from like a week ago or a month ago, or we all have really old tabs. This way, they haven't been consuming your bandwidth every time that they've been doing nothing with your site. So you can pause your provider, and then when the tab becomes visible again, you can resume, and you get the choice of whether you want to replay all the events that would have happened during the time that was paused, or whether you kind of want to just drop them and keep on going. Both situations have like valid use cases, so up to your own personal use case. The cool thing with this feature is because we can now pause and unpause providers, all the underlying API and framework changes that went into making this happen, it means that if you have, for example, a WebSocket and the WebSocket disconnects, it can now reconnect and resubscribe to all your events before it starts feeding you the new events that start coming in. It can actually get the events that happened from the time it disconnected to the time that is now. And so all your events come back in order, and you don't miss a beat, and you don't even know that your WebSocket crashed. And odds and ends. I'll just go into these quickly. Basically, networks are now a plugin. They have a plugin system. There's a lot of really strange networks out there, and I always get like requests saying like, oh, my network computes hashes in this strange way, or my network doesn't have an author in the block, or this sort of thing and the other. So this makes it possible that ethers can stop capitulating to each of these individual things and all those oddities, which are fine. I mean, competition in the ecosystem is good, but then we can like push all those differences into the network object and let it handle it. And package exports. I'm moving away from a mono repo which uses a bajillion sub-packages all by ethers, because it used to be like @ethersproject/ABI, @ethersproject/providers, and that sort of thing. Package exports are awesome. They're supported by all major bundlers now, and it means that there's no complicated, weird process going on for Ethers build. For those who've used Ethers or tried modifying Ethers at all, the build process is absolutely insane, because I try to target, again, ES3 and React, and I try to build for everything, and as a result, people who are using more modern utilities, like people complain about Vite a lot, or if you're trying to build a bundle for Node, it just fails. So the nice thing is by using package exports instead of all this crazy custom scripts, it just kind of works with all these tools, and everyone's happier. I hope we'll see that after I launch the non-beta. There's better and fewer dependencies. I'm actually going to grab a bit of water. So yes, there's basically, I think I'm at 5 dependencies-ish right now, but down to 4 authors, which is an important thing. I feel like we've all like recently been pretty worried about like supply chain attacks going on from NPM installing a bajillion things, and so right now there's 4 well-established authors that are responsible for all the libraries. So there's me. I consider myself well-established. There's Paul Miller, who does an awesome library for hashing and for signing, and Microsoft writes TSLib. It's a tiny little thing. It just helps save some space. And WebSocket, there's a popular WebSocket library that works in Node. If you're using a browser, you don't even have to use that one. So now you're down to like 3 authors and 4 dependencies. And it saves me a lot of work as well, because there's so many times where like Elliptic has some bug in it, and I'm trying to track down him to get him to update things, and once that's fixed, I now have to update everything and put a new build out. So the fewer dependencies, the happier my life is as well. And that's all I've got. I've got 9 minutes for questions, if anyone has questions. Oh, and come find me afterwards. I've got these little like, I brought one up. For anyone who's like curious about V6, I've actually started to write, I should explain that. So yes, basically, I'm trying to write a bunch of little apps right now against V6 to help test it. So this one's actually found quite a few bugs already. It's an NFT. It's got a little scratch-off hologram. When you scratch it off, you can scan it and claim it, and you can fold your little papercraft robot up and like do this, and then take pictures of him and post it into the contract, and you can like, I'm thinking of it more of like that little gnome from Amelie. You can take it around and show you that this thing's visited different places. Right now, it's only deployed to Goerli. For anyone who actually like goes through the effort of like submitting this, I will be migrating your tokens to mainnet. If you want to wait till the mainnet version launches, the same QR codes will work on mainnet, and you can claim it there. So that's just like a little demo I'm throwing together to test and make sure V6 works. And it's definitely not ready for production as it stands right now, but it's getting closer, and I'll probably be doing a few more little weird projects like this just to kind of like find those little foibles and things that happened during the last 2 years worth of rewriting and rewriting and rewriting. So I've got 7 minutes, 49 seconds left for if there's any questions out there.
When you say you manage strange networks, does that also mean, for example, Celo?
Yes, I think Celer is one of the ones that has, do they have a different way of computing the transaction hash? Yes. So I think they're actually one of the ones that was like an early headache that led to the reason for me trying to put that stuff into some place that was a little more isolated from like the core providers. So yes, Celer is I'm 90% sure one of the ones that, yes. Oh, go ahead. There's lights. I can't see. I'll trust the moderators to hand out mics and ask questions. And just maybe jump and swing your hands if you're...
OK.
Oh, there you are.
Yes. First of all, oh my gosh, thank you so much, Richard. I don't know where we'd be without you. Like, you're open source hero.
Thank you.
Yeah, so, again, thanks so much for all you do. The ecosystem would not be the same without you. But just curious, like, at this point in the state of Ethereum, at this point in the state of Ethers, what kind of support are you getting in terms of, like, audit help, especially as we see more, like, front-end attacks and things like that, right, where it's like, smart contract auditing is important, but the interaction layer is equally as important, especially now as people are getting more clever, not to throw shade, but like when I saw string normalization for ABI calls, I instantly thought like just made me like uncomfortable in my gut of like different things that could happen. So just curious, like who's helping you audit, who's helping you kind of like comb through this code and go through different edge cases and things like that.
Right, so basically auditing is all done by me, which is terrible right now. One of the cool things though is I've got like, the EF helps sponsor me. I get GitHub grants, Gitcoin grants, and I have a few sponsors. And so now I'm starting to develop an endowment. So I am hoping to be able to get like a proper audit at some point. There was one team at one point that was going to formally verify a bunch of things. I haven't heard from them in a while, so I don't know if that's still a thing. But I think I'm on the fence with formal verification. Like it helps in some regards, but it's not a magic bullet. I think absolutely like proper auditing would work, and I'm also that's why I'm a big fan of tests. I don't want issues to happen. So I feel like tests can only find the presence of bugs, not the absence of bugs. It's a great question. Talk to me afterwards if you've got some ideas. I'm starting to get some money off to the side now that I can actually start throwing, if you know any like auditing firms that do TypeScript. What do you mean? You should definitely pay for auditing. Those people are so skilled and valuable. Oh, okay, sure. Well, you kind of are. Thank you, Gitcoin. Gitcoin's been awesome. So.
Here. Hi.
Oh.
I was wondering if you are gonna add batch transactions in this version.
Sorry, it's a little bit hard to hear with the echo. Are you asking about batch JSON RPC?
Batch transactions. Sorry.
Oh, batch transactions.
Yes.
What do you mean by batch transactions? Like via smart contract wallets?
Sorry?
Like you mean through smart contracts or?
Yes.
Yeah. That already works. You just need the ABI for it. There's not currently in Ethereum an official like batch standard, but you can do it with smart contracts, like smart contract wallets, like a Gnosis safe, for example, allows you to send multiple. Is that what you mean? Like being able to send multiple transactions at once, atomically? Sorry.
No. I have an application, and I want to send a batch of transactions in my Node application, not through contracts.
Not through what, sorry?
Mm-hmm.
Oh, not through contracts. You can't currently in Ethereum in general send multiple transactions atomically or at once. You basically, if you have a bunch of transactions you're trying to send serially, so the nonce manager already does that. Basically, it's a wrapper that goes around a signer, and you can just quickly fire off transactions, and it will automatically bump up the nonce from the initial nonce it fetched. There are some issues with that as well. If you just flood the mempool with a bunch of transactions from the same address that are all serialized, it could be seen from the network's point of view as a DOS attack, and so it might drop them. So that's a feature I want to add to the nonce manager in V6 as well, is kind of the ability to rebroadcast, or whenever something succeeds, kind of like have a callback that lets you know something succeeded. And so you can kind of nudge or tell it to rebroadcast the transactions that are still around. I think if I understand your question. Thank you.
Hey, Richard. Can't understate how useful what you did for the whole Ethereum community. We use what you do every single day, back and front end, everywhere. So thanks for that. Really,
thank you.
Thanks.
Yeah,
So yeah, more than deserved. One question about philosophy, and this is going very specific. I'm being that guy. But one thing that Ethers has a philosophy is really how it returns undefined, and actually it doesn't return undefined for waiting for transactions. And we actually talked once in one of the PRs of TypeScript really giving the option of returning an undefined when a transaction, you wait on it and it doesn't return anything, for example. And you mentioned that that's not really part of the philosophy of how you're building the types for Ethers.
Sorry, I missed that last part. So you mean when you set a transaction and you get back null, or?
Well, let's say it's a hash that doesn't exist.
Okay.
What is the philosophy of Ethers returning that? Would it be undefined? Because in their case, the TypeScript for that doesn't contain undefined. It always says.
I know what you're talking about now. Okay,
yeah.
so that's a big thing in v6 as well. I should have probably put on the odds and ends. Okay.
We4 came for exactly that.
Right.
So.
Right. Okay. So for quick background, basically Ethers v5 was started 2 years ago. I was still kind of learning TypeScript. It did not have strict null checks enabled, which basically means anything that returns anything, always return that anything or null. And so in v6, I've got strict null check typing and strict null check type, whatever what the flag is. It's enabled. And so, for example, the provider's method for get transaction, it will be, the return type is null or transaction response. Whereas in v5, it was just transaction response, and I just trusted people knew that it could be null, but don't worry about it. So yes, v6 has been fixed. It helps fix a lot of other people's libraries as well that are like dependent on it and are kind of crawling into the Ethers tree to like run their linting rules. So yes, that's absolutely changed.
Will there be backward compatibility between the big int type and the big number type?
Sorry, I can't see your.
It's better now.
Oh. Hi, I see you. Yeah.
Will there be backwards compatibility between those new big int type and the old big number type? Like, will big int be big numberish?
Sorry, will what be big numberish?
The new big int type.
Oh yes, big. I mean, for input types, you mean?
Yeah.
Yes, there's still a big numberish type because, so for example, the slide up there that demonstrated. I lost the clicker. The slide that shows you. Like the transaction.maxgas equals, so that takes in a big numberish. So you can pass in a big int, you can pass in a string that happens to be a decimal number, you can pass in a string that's a hex number. That'll all be munged into a big int type, but you can still pass anything that's not ambiguous, Ethers will accept. It will not accept things that it can't possibly interpret, like, for example, non-0x prefixed things, because if it did that, it wouldn't know whether 1, was hexadecimal 17 or binary 11, and so it requires you to be completely non-ambiguous. So if you pass in a string that's 1, it's going to assume it's decimal. But yes, it's still a big number. It's still a big number-ish. And there's functions as well for your own purposes that will convert any big number-ish into a big number, or any numeric, which is another type that it now has, into a number. I've got 22 seconds left. And also as a quick note, I'll be standing outside after this for anybody else who has like questions to like poke around.
It will not be enough. 20 seconds.
Okay. I'll see you outside. I'll be handing these little cards out as well, and like so. Thank you.
Thank you so much, Richard. Guys, make sure to collect the cute robot. I definitely want one. All right. That brings us to our last talk for today in the developer infrastructure category before we move on to some zero-knowledge stuff. So I'm excited to introduce Potus. He's a core developer at Prismatic Labs, and he enjoys the types of puzzles that arise when trying to hack the protocol. Today, he'll talk about the right way to hash a Merkel tree. So please give it up for him.
Thank you. Would you happen to have the clicker? There he is. Thank you. Thank you. All right, so thank you very much for letting me speak here. This is going to be a very different kind of talk, and it's my first talk in this community, so expect something. I don't promise anything. I just want to sell you something. I just want to get right to it. I want to tell you this. If you're hashing, if by any chance you need to perform hashes, that this happens quite a lot in the consensus layer, I want to tell you this library that will hash at the very least, it will hash 20% faster than your current backend without any changes to your code. And if you see here in the bottom, do I have a pointer here? I guess. No, this is just a click. OK, so if you see here in the bottom, you see that for large trees, this is hashing 4.5 times faster than the common backend. So I just want to tell you this. And since I can tell you in 2 sentences, I'm going to spend most of my talk just telling you what is SHA-256, which is what this library does. But the techniques of this library can be applied to whatever other hashing on the SHA families that I know of. So let me tell you what SHA-256 is. So let's start with this slide. The hashing library is something that generically just takes any message, an arbitrary length message in a sequence of bits of any length, and it just spits out of that 32 bytes. The digest of this thing is 256 bits. And the procedure to go through those consists of 3 parts. So I'll just go over the 3 parts briefly. The first part is breaking your message into multiples of 64 bytes. So those are the chunks, 512 bits. The second part consists on scheduling words, computing a bunch of double words, which are 4 bytes each. And the third part consists on performing a bunch of rounds, which is just the function that actually does the hashing itself, the function that is not invertible. So here's just a brief description of this slide I just stole from somewhere in the internet. But I want to go in some detail in each one of the 3 parts. So let's start with the easiest one, which is scheduling words. So scheduling words, as you see here, you're given a message. Let's suppose that we've already broken the message in pieces. Each one of them is 64 bytes. So the first thing you do is you compute 48 double words, 4 bytes each. You need 64 in total. The first 16 are your message, are the 64 bytes that you're giving. These are 16 words. And with those 16 words, you can compute the next 16 words. And with those 16 words that you just computed, you can compute the next ones, and the next one, and you computed the 64 that you needed. And the important thing that you need to remember from this slide is that to compute those scheduled words, the only thing that you need is the previous words, nothing else. That means that when you're scheduling words, well, I think the consensus people are starting to come in. Anyways, I've already started, guys. So when you're scheduling words, the important thing is that you don't need to know the previous state of the hashing. You only need to know what were the previous scheduled words. In particular, it only depends on the chunk that you're hashing now, and it doesn't depend on the other chunks that you're going to hash. So if your message consists of 10,000 chunks, you can compute the scheduled words for the 10,000 chunks without caring about how you would hash each one of them, and without caring about the rounds part. So scheduling words only requires the previously scheduled words. So the diagram there is taken out of an Intel paper describing what were 2 new instructions that do this scheduling of 4 words at a time with only 2 instructions. This can be done now on modern CPUs. And this is just a sketch that how diagrammatically you compute 4 words at a time. But it's irrelevant the method that you use to compute those scheduled words. What I want you to remember is that to compute them, you need to know the previous words and nothing else. Rounds, we don't care about what rounds is. We only care that it's a function that is not invertible, that is hard, that is computationally hard to invert. But the important thing that we need to remember is this. We were given the message, we broke it into pieces of 64 bytes that I haven't told you how. We computed those scheduled words that we need, and then what we do is we pass an incoming digest If it's the very first chunk that you're hashing, we pass a constant digest that the method has. If it's the third chunk, you're going to pass the hash that the second chunk produced. The point is that you have a status, which is your current hash, and you pass it through this function that takes this status, the hash, the 32 bytes. It takes one of the scheduled words that you computed, and it takes another constant word that the protocol has. So it takes this data, and it produces for you a new hash. So what do you need to remember from this is that you need to have computed at least that scheduled word before passing through the rounds, and you cannot do this in parallel. To pass through the round, you need to have computed already the hash before. So this is something that you cannot do in parallel. Okay, so the padding block. So this is the first part of the three process, which is breaking the message into multiples of 64 bytes. How do you do this? Well, you just break your message into multiples of 64 bytes. You add 1 bit at the very end of the message just to signal this message has ended. So here the message is less than 64 bytes, is 24 bits. These 3 bytes there, A, B, and C. This 1 there is showing that we added that extra bit to show the message has finished. And then you pad with 0 bits up to a multiple of 64 bytes minus 8, because you're going to use the last 8 bytes, or 64 bits, to encode the length of the whole message. As is there in binary, that's the number 24, which is the actual length of this message. Okay? So this is the procedure to pad your message, which was arbitrary length, into a multiple of 64 bytes. All right. So vectorization, which is the main topic of this talk, is vectorization. So the first thing to notice is that you're not going to beat any of the hashers out there. Every implementation that I've reviewed before I got into this, and I'm not an expert at all on this, I'm come from a completely different subject, but every implementation I've seen is equivalent to Intel's original white paper on this, and it's equivalent to what OpenSSL, for example, does. All of them implement the following. You can compute your scheduled words, as I told you, without knowing what the previously hashed, what the current status of the hashing is. So all of them use vector instructions to compute several words at a time. If your CPU supports 128 bits registers like these ones, and almost every CPU now does, then you're going to compute 4 words at a time, 4 double words at a time. You start with your 16 double words, which is your message, and you can put those 16 double words in only 4 registers. If your computer supports AVX2, it can do arithmetic in registers that are 256 bits, then you're going to compute 8. You're going to use only 2 registers, and you're going to compute 8 words at a time. If your computer supports AVX 512, you're going to compute all of them, the 16 of them at a time. And, well, AVX 1024 does not exist yet, but it's already in the books. There's 2 options into computing this. Modern implementations either do this vectorization, or if your CPU implements cryptographic extensions, like what was there in the picture, then they will use 128 bits registers, regardless if your computer has larger registers, because cryptographic extensions can compute 4 words at a time much faster than vectorized computations. But the point I want to make is that this vectorization is there in every current implementation. This is since Intel's white paper. Also, computing the words like this is useful because since you can compute the words and at the same time pass through some rounds, so let's say that you computed the 5th word, then you can pass up to the 5th round. Then you can mix scalar operations with vector operations, and the CPU will perform this in parallel. The CPU has several ports and can take different types of operations at the same time. So you can be computing the 5th round. That is a computation that it has to be done on the scalar part of the CPU because it has to be, it cannot be in parallel. And at the same time, you're computing the 6th word in parallel on vector registers. Okay, so I've covered what is a typical implementation of hashing. And this is the thing to remember from the whole part, from the whole third parts of the talk, is that the hasher signature is this. In either language, it's something like this. It's something that takes an arbitrary length byte slice, and it gives you back 32 bytes, which is the hash. Okay? So it takes an arbitrary length message, and it gives you the digest. And this is something that you're not going to beat. You're not going to implement this better than OpenSSL. No one's going to do. You perhaps can do it for one CPU. You're not going to write an implementation faster than what is already there. However, we use hashing in a very restricted scenario. We use hashing to hash Merkel trees. And Merkel trees are not arbitrary length. Merkel trees are, in the case of the consensus layer, for example, where the nodes are 32 bytes, there's something like this. Each one of these nodes represents 32 bytes, and each parent node has only 2 children, and these 2 children are hashed together. So the 2 children are 64 bytes and concatenated. You hash them, and you get the hash of the parent. You get what goes in the parent. So this is what we hash, typically. And we observe 2 things. Well, actually, the execution layer has something completely different, but still, the same technique is going to apply. What we observe immediately is the following thing. First of all, we're not hashing arbitrary length. We're hashing every single time 64 bytes. And second of all, we can hash this in parallel. You don't need to, you can hash the blue one by knowing the entire left subtree and hash the yellow one completely in parallel in the other side. Of course, you can do this in parallel if you have a CPU, if you have 2 CPUs, you can just use 2 threads to hash this. And this is exploited in the consensus layer. I don't know if any other besides Lighthouse uses this. But I want to use this, I want to talk about a different kind of parallelization. You can parallelize this in different threads, but the point I want to make is that you can do this by using vector instructions. So again, this is the typical, this is the one that is in the specs, in the consensus layer specs. This is the implementation. I think this is Vitalik's implementation. This is a flat array approach to having a Merkel tree. I highlighted the line where you're computing the hash of the parent by hashing the 2 children that are concatenated. The top one is different memory layout. This is Proto Lambda's implementation on Remarkable. The point is that it's the same kind of hashing. You take the 2 children and you hash them, and you hash 2 blocks at a time. This is fairly inefficient. This is a Go implementation. This is also Jim's implementation. This is a production implementation. And again, the same thing. It's slightly more complicated because it takes into account other things. But the highlighted line is the point where you're hashing, and you hash 1 node as the hash of the 2 children. And you do this on a loop. For each pair of children, you hash once, you call the hasher, and you get 1 hash. Okay, so I want to tell you what is the right way of hashing a Merkel tree. And it's fairly simple. So there's 2 things that we want to exploit. We want to exploit the fact that this takes an arbitrary byte slice, so this is the layer that you want to hash, and it gives you back a slice of hashes of 32 bytes. So it hashes all of them at the same time. I think I might have gotten this correctly in Rust after several iterations. This would be in Python. We have a library. We have 2 libraries. We have one in Go assembly, and we have one in usual assembly with C bindings. If you are going to use that, let me know, because crypto extensions on ARM is still not implemented. It's going to take like 10 minutes to add this. But this is the signature that the library is going to use if you're using a C bindings. All right, so that's all I wanted to tell you, and that's it. Sure.
Taking questions?
Sure.
Yeah. Sorry we were late, by the way. It was really hard to get in because there was a...
I think we started even before the hour scheduled.
Yeah, cool. So the ability to hash different values in parallel, that doesn't exist in libraries already, is that right?
It does. So Intel has this library where you give them different messages, and it hashes them all at once. So that, I just copied everything. Nothing here is mine. I just grabbed Intel's implementation and Bitcoin's implementation and put it in a library. The thing with Intel's is that it takes arbitrary length things, and it just hashes it, and it gives you back just the hashes for all the messages that you give him.
Okay, sure. I'll just repeat that for the sake of the recording. I was just asking if the ability to process multiple different hashes in parallel was already implemented in libraries. That was the question to the answer. So there's two things that you have here, right? One is to like pre-compute the padding block, and then the second is the ability to in parallel process multiple different hash values and then produce multiple different hash values, right?
Correct.
And so there are already implementations that do multiple different hash values at once, and you just modified them to deal with the padding block. Is that right?
Yes, and yes. So there are two modifications here. One is the thing that you're going to use the padding block. The padding block has this constants hard-coded. And then there's other modification, which is the fact that you're expected to get a list of 64 bytes chunks, and then you pipeline this. So what this library does is it grabs all of the blocks consecutively in memory. It gets a matrix on the vector registers. It transposes this matrix, and now you have on all of your registers the different messages. So then you can use Intel's machinery to hash those messages in parallel. You output these hashes, and then you just loop it back. So
okay, cool. So you have, so the result is basically so it's in Go assembly what you have, right?
Sorry?
Your implementation is in Go assembly.
Yeah, so the original implementation was just purely assembly. This is there. It has C bindings, but the C Go overhead is horrible. So it ended up being slower than using the Go implementation, the standard library in Go. So we needed to write a Go assembly library to use ourselves.
Yeah, okay, cool. Well done. Very good, very impressive.
Thanks. Oh, Peter.
Okay, I'll just say, I wonder, after you've done this, have you considered whether, I don't think this is practical, but it would be interesting if someone tried to design a hash function specifically for hashing Merkel trees, and whether they could do it differently, and how big the savings would be for that if there was like a special hash function for Merkel trees?
I'm sorry, I didn't get this. So
I'll repeat your question. So I was curious, you've shown that there are all these optimizations you have to do to get around the general purpose nature of these general purpose hash functions. Do you think it would be possible to design a hash function that was like a special hash function only for like hashing?
Oh, that's a good question. And I believe, that's a very good question. I need to think. I don't think I can answer this here. I'm not sure if you can do better than the current implementations. Like you can take the sponge type implementations, SHA-3 and company, and you can try to adapt this for this. I don't know. I think, yeah, your question is completely open. It's a very good question. I think we should think about this. So if I understood your question as, can there be a method that is designed for Merkel trees instead of like a generic one? It might be. I don't know.
Sorry to hog the mic. In your implementation, does it, so say there's some really big Merkel trees in the beacon state, right?
Yeah.
Is it the job of the implementation to kind of split that Merkel tree up into smaller subtrees that fit the size of your CPU?
No. So you're saying if you have this large tree, if it's the job of the implementation in splitting into smaller trees? No. This is completely orthogonal to that. So what you guys are doing in Lighthouse is splitting this into smaller trees, and you send this on different threads to compute them in parallel. This is completely different. You just pass the entire slice. So big trees is the big gain for this. You're going to be at least hashing 4 times faster than the standard library. You just pass the entire slice, like all of the slice of the bottom slice, and what this thing is going to do is not split into subtrees. What this thing is going to do is grab as many blocks as possible that it can fit in your registers. And then just go to the next chunk, and the next chunk, and the next chunk, and like this. So it doesn't split in subtrees.
Okay, and so you feed it all of the leaves, and then it produces the intermediate leaves.
It produces the next layer, and then you just feed it the next layer entirely, and it produces the next one.
Oh, yeah, I got you.
So for the state, so you're thinking in the beacon state. For the state, this is incredibly fast, but this is not how we hash the state because we have it in cache typically, and you just have a few nodes that you're changing. So when you hash the dirty trees, the dirty leaves, then, well, there's two things that happen. So sometimes you have several of them that are consecutive, and then you can be smart and pass this consecutive layer to this hash. Or you can just use whatever you're using now. Just hash 2 blocks at a time. You're not going to get the vectorization impact, but you're going to get at least the 20% of the hard coding, the padding block.
Yeah, okay, cool. So I guess there's maybe like an argument for maybe it's quite useful for small trees. You don't get a lot from caching.
Yeah, it's not really useful for small trees. You only get the 20% of the padding block.
Yeah, okay.
It's very, very useful on large trees. And here, large means more than 8 blocks. So anything that has depth more than 2, this is already 4 times faster.
Nice, thank you.
Thank you. Just in time.
Thank you.
Thank you, guys.
All right, since we are still very good on time, I am going to use a few minutes to talk about something else so that the ZK people have time to come in as well. Yeah, first of all, if you want to ask questions, please do wait for the microphone because there is also a live stream and people can only hear the questions in the live stream if we use the mic, and also for recording purposes would be nice. Thank you. Secondly, this year in DevCon we're doing a couple of things different than we used to do. We are very experimental in some ways, which I'm kind of excited about, so I will use some minutes to talk about this before I hand over to the next speaker. So I'm not sure if you guys saw it on the website or maybe on Twitter or in some of the communications around, but this year we have introduced something called Continuous DevCon, which is basically our way towards a more holistic, decentralized, community-driven DevCon. And as part of that, we are trying out various concepts, one of which is that the venue will be open until 11 p.m. So if you want to meet up with somebody, if you just want to have, I don't know, a catch up with somebody, if you don't feel like partying, if you want to hang out here, feel free to use the venue. And yeah, basically the basement, the first floor, and the second floor will remain open until 11 p.m. Also, there's a happy hour from 6 p.m. to 8 a.m. in the first floor, so feel free to mingle there as well. And then lastly, in order to make everything a little bit more community-driven, we have allocated a space on the first floor to 6 selected communities, and it's called Community Hubs. So in there you can find various different spaces that are run by communities, one of which being the Region Hub, the Temporary Anonymous Zone, the ZK Community, the Crypto Governance and Economics Hub, Crypto Economics and, what was it again? Token Engineering Hub? I don't know. This is powered by Token Engineering and Smart Contract Research Forum, and the Women Leaders in Web3 Hub. So yeah, a lot, and the Design Hub. So lots of stuff to explore there. Please feel free to check it out. And lastly, the Hacker Basement. So we transformed the parking lot, which is in the basement, into a hackerspace. And it's definitely worth looking at it because it really is beautiful, first of all. Secondly, there is also some sort of art exhibition going on in there. And thirdly, if you want some quiet time, if you want to hack something on your computer, or if you just need like a break from the masses, I can really recommend the Hacker Basement for all of that stuff. Yay, okay, I think now we can move over to the ZK part of the day. First, I'd like to introduce Thibaut. Thibaut is building Socrates at the Ethereum Foundation, and today he will give us an update on, surprise, Socrates. Socrates is a toolbox and a set of tools aimed at making developing ZK Snark applications easier using a high-level language. So please give a warm welcome to Thibaut.
Okay, thanks, Francie. After so many great talks from the development tools track, my goal on this talk is to convince you that this is not moon math. This is also development. This is also tooling for developers. So today I'm going to present Zokrates. I'm going to give a quick introduction to what it is for those of you who don't know it. And then I will present a few things that we've been working on and that I'm excited to share. So what is Zokrates? So if you want to program snarks today, there's different tools that you can use. Maybe some of you have heard of Zokrates, of Circom, of Halo 2. And all those tools have different trade-offs in terms of the power that they give to developers and how easy they are to use and how high level or low level they are. Zokrates has a positioning as a very high level language. So when you write Zokrates, it looks very similar to if you were writing Rust or Python or something like that. It compiles to R1CS. So this is the kind of snarks that are easy to verify today on Ethereum. So you can verify directly in your smart contracts. It uses modular backend implementations, which means that Zokrates does not develop a proof system itself, but rather uses backend implementations from the community for different proof systems, and just targets that and uses those great implementations. In order to have such a high-level language, but still have something that's really efficient at the low level, Zokrates makes use of optimizations in the compiler, which is something that's also different from some other tools, which give you a very low-level access to what's going on the constraint level, but don't really apply a lot of optimizations. So where does it run? So the part of Zokrates which allows you to compile, so the compiler, you can run it natively on your machine. We have a Remix plugin as well, and we also now have a playground that you can access at play.zocrat.es, which I encourage you to start. That's probably the easiest way to get started with Zokrates and just write some simple programs. In terms of the scheme, so there's backend implementations that we support. We currently have support for Graph 16, which is, some of you may know, the snark that is the smallest and the fastest to verify. For GM17, which is an evolution of Graph 16, let's say. For Marlin, which is a universal snark, which I'll touch on a bit later. And for Nova, which I'll also go into, which is a new type of exciting snark that enables new use cases. For proving, so the particular implementations, we rely on Bellman, Arc, Bellperson, and also Snark.js. I'll also go into a bit more detail on that integration. And in terms of the verifier, we have, you can verify in JavaScript or in the CLI. And for some of the schemes that are compatible with the EVM, we generate a verifier contract so that you can directly send your proofs to your smart contracts and verify them and link them to your dApp. So to give a bit of a hello world of Zokrates, here's a program which takes two private inputs, A and B, and one public input, C, and then asserts that A times B is equals to C. So technically, this is a program with which you can prove that you know the factorization of a number. The way you would run that is you would first compile that program, which would turn it into this low-level representation that's, let's say, R1CS. Then you could execute that program with an input, here 3, 3, and 9. Then you could generate a proof using a particular proof system. And you could also generate a verifier that you can then deploy on the EVM and then send your proof to and then basically convince the network that you actually knew this factorization. For an example of something that's a little bit more advanced, to make the point that this is actually a high-level language, here's the implementation in Zokrates of the SHA-256 function. So just to give you a few things that are expected in a high-level language, we have a module import system. You can import constants as well. We have for loops, of course. We have function calls. And also one exciting thing that we added kind of recently, and maybe some of you who use Rust are familiar with that feature, is the notion of constant generics. So in this case, the SHA-256 function is a hash function that can take an arbitrary number of bytes as input. However, in circuits, all the inputs are always static. So all of these, the size of the input will always have to be known at compile time. But this is something that we do. You can still define this as something that is generic over k, and then have a number of rounds of this SHA round function. But then when you compile your program and actually use the function, the SHA-256, this variable k is going to have a concrete value, which will then compile to the exact number of blocks that you're hashing. And if you're trying to do something that's dynamic, calling this function on something that's not, whose size is not known at compile time, is just going to fail at compile time. So we can have a very idiomatic implementation of SHA-256. Of course, there's more complexity in a SHA round. But if you look at the code, it's almost line-to-line equivalent to an implementation that you would see on Wikipedia, for example, a pseudocode implementation. Now I'm going to go in a bit more detail on a detail of the SHA-256 implementation. So inside the SHA round, there is this expression needs to be calculated a lot of times. It basically takes three unsigned integers, a, b, and c, of 32 bits, and calculates a and b, XOR a and c, XOR b and c. And this is something that you can just write like this in Zokrates today, compile, and it will translate that to a number of constraints at the low level. However, if you do the math and look at let's say the first bit of A, the first bit of B, and the first bit of C, you can see that if you consider them as numbers, so as field elements, they actually verify, so the result actually verifies those two equations. So you define, or you constrain a new variable BC to be equal to B times C. And here, I just want to clarify that these constraints are the low-level constraints that we deal with. So the R1CN's constraints, they look like this. They have one side which is linear. So in this case, it's only one variable, but you can have a sum of different variables. One side which is quadratic, right? So this first one just defines BC, or like constrains a new variable BC to be equal to B times C. And then introduces this res variable here, which is our result for the first bit. And then constrains it in this way. And this is actually more efficient than what the compiler would generate itself, because here we have more knowledge of what we're actually trying to do than the compiler does. On the flip side, here, what we're doing is that we're introducing a new variable res and then constraining it with this equation. However, when you're dealing with such low-level details in snarks, it's really easy to introduce new variables, but fail to constrain them sufficiently so that you actually introduce vulnerabilities in your circuits. So this is something that Zokrates does not expose at the moment to the developer, which means that you can only do this one, which is less efficient. If you look at more lower-level tools, they let you use these things, but then it's at your own risk. And then it's likely that you're going to introduce vulnerabilities. So what I want to showcase today is the addition to Zokrates, a way to actually encode this thing and have the performance from this thing in the context of the higher level language. Yeah, so I have a video now, if you could start the video. Right, so this is using actually the Zokrates playground. So here I defined the default function, which I call the default function, where I'll just use the compiler to generate the constraints for this, this expression. Here I'm going to create an entry point for this program, so taking also A, B, and C, returning a U32. And I'm just going to call the default function and see how many constraints are created in the process. So I compile, and then I get the result, 260 constraints here. And now what I'm going to do is to define another version of this function, which hopefully will reduce the number of constraints by leveraging this lower level implementation. So I call it hand optimized, has the same signature, A, B, and C. Also return a U32. So as I described earlier, I want to operate on each individual bit of those U32. So the first thing I'm going to do is turning those U32 into an array of booleans. We have sort of a magic tool in our standard library to do that, which is called a cast function, and which can do this conversion for you. And here I want to point out that this is actually free, because the U32 type is actually represented as 32 bits under the hood. So we're not paying any constraints for this. So I just cast the three of them. The next thing I'm going to do is introduce a new array of booleans for the result. Here, one relatively new feature we have is that everything is immutable by default. So here I have to declare this variable mutable if I want to be able to modify it after. OK, so now that I have all the bits, I can start a for loop. So for I from 0 to 32. And here I'm going to consider the ith bit of A, B, and C. And if we want to have access to those low-level constraints, we need to reason at the level of field elements. So we need to turn those booleans into field elements, which is a lower-level representation. For this, I call this bool-to-field function, which I'm going to define in a second. I do the same for B and C. And here, I'm going to define this function. And again, this is something that's going to be free. It's not going to create any constraints for the same reason as earlier, because a Boolean is actually represented as a field element at the low level. It's just that it can only be value 0 for false and 1 for true. So I can just return that using a ternary expression. OK. So now I have A, B, C as field elements. Now I have this first constraint, which was BC equals B times C. And actually, this constraint I can already define in the high-level language, because I'm doing both constraining and assigning BC. So I do that. So I have that first constraint is done. Then I declare this result, again mutable. And this is where the interesting new thing happens. I have this assembly block that I can create, and here I have access to two special kinds of statements. The first one is going to be just an assignment. So I just assign the value BC minus this other expression to res, but I did not create any constraints. It's purely just an assignment. So this has no influence on the constraint system. And then I want to be able to use this res value later, but to use it, I need to make sure that it's really constrained in the constraint system. So after this assignment, I add actually a constraint, which makes sure that everything is set in stone. So here, BC minus res equals this multiplication. You can see that, again, this can be any expression here when I assign, but this has to be linear equals quadratic, right? So here, this is working. OK, so now I have everything set up, and I'm convinced that res has the result that I need. The next thing that I want to do is that I actually want to have a Boolean. I'm going to go the other way around and reconstruct my result, but I want to have a Boolean, and I want to go from a field element to a Boolean. And here, I want to make it really clear that this is a potentially unsafe operation, because this res value, I know that it's 0 or 1 because I wrote this, but in theory, it could be any value. So I need to be really careful when I do this. But I can force the creation of this Boolean with this value. Finally, I reconstruct the U32 value from the Boolean array using this cuts function again. OK, and I changed my entry point to use the hand-optimized version. So we were at 260, and now we're at 164. So we made quite a big dent in our constraint count. OK. Oh, can I exit this? OK. So what's the idea here? We want to keep all the guarantees that we have from our higher level language. We have types, we have things. We know that Booleans can be only 0, 1 if you don't write assembly blocks. But at the same time, we want to have access to this low-level thing. And here, I think there's actually a parallel with Rust in a way, which says, OK, we have a compiler that's like really strict for all these things, but we still want to be able to do all these lower-level things. We want to disable a bunch of checks. And we have a similar approach, where as a developer, you would write most of your program in safe Zokrates, let's say. But then for the few parts that need the extra performance, you can write them in those ASM blocks and try to make those blocks as small as possible so that when you need to review the code or make sure that things are not unconstrained, you know exactly where to look at, and these things are relatively small. One side effect of this, also for us as a compiler team, is that we can use this ourselves to reduce the complexity of the compiler. So this particular operation in the SHA-256 algorithm, in the compiler, we have a special case which detects whenever we're doing this and uses this exact constraints. But now, potentially using assembly blocks, what we can do is rewriting some of the internals of the compiler to actually use these things, which then reduce the size of the compiler code base and makes it easier to reason about and audit. OK. The next thing that I want to talk about, which is unrelated to this, is the fact that Zokrates is not compatible with Snark.js. So Snark.js is a JavaScript library for snarks from the ident3 team, from the Circum team, which has a bunch of tools allowing you to work with snarks in a JavaScript context. So what we have now available today is if you start from your Zokrates program and you run compilation, currently it returns an output which is the low-level Zokrates representation. But you can also optionally return an .r1cs file, which is the format that is accepted by Snark.js. And then if you want to execute your program, you take your input and the program itself, and you can create a witness file, which is also compatible with Snark.js. And from this point on, you're in Snark.js land. So you can do whatever Snark.js enables you to do, using different proof systems, using a parse of tau, ceremony, and run your verifier in the browser, et cetera, et cetera. So any tooling that's compatible with these formats can now be used with Zokrates as well. Another topic that I wanted to touch on quickly is incrementally verifiable computation. So this is a scary word, but it's basically the idea that if you have a computation which you can split in steps, which are basically the same function being run over and over again on the state and updating the state, then you can actually use recursive snarks to prove this computation incrementally. So as opposed to Zokrates currently to other proof systems where you can think of them as more like an ASIC, so your circuit is like this ASIC that's really set in stone and you can do only one computation and everything is bounded and static. In this case, you can have a computation where you run one round of the computation and then another one later, and you can prove the execution of that computation at each step. So some use cases for that are succinctly verifiable blockchains. So maybe some of you have heard of the Mina blockchain, where basically you use this to have a blockchain where each time you get a new block, you verify the previous block as well as the transaction of this block, and it creates a snark, and then you have this kind of recursive verification. Another use case is VDFs, because some of the VDFs actually have the structure of having some state, which is then to which you apply a function recursively, and then being able to have snark of these computation can be really, really useful. So what we're working on now, and we're actually pretty close to having this ready in production, is integrating a proof system called Nova, which does exactly this. And the way that I'm not going to go too much in detail here, but the way that the API would work for developers today is that you write a function, and the only restriction here is that the input needs to be the input type needs to be the output type, because you want the recursive aspect to work. And then you can compile this function to a specific curve. So you need to use this Pallas curve, because under the hood, Nova uses cycles of elliptic curves. So this doesn't work for any curve, but we support the curves that enable that. And then you can basically prove a number of steps starting from a given state. And even after running this, you could run it again starting from the last state that you had. So this opens a lot of use cases for people who want to experiment with incremental verifiable computation. So I invite you to test that. It's going to be out very soon. OK. Since I only have 2 minutes left, I'll just go very quickly through some things that we added recently. So there's the powers of Tau ceremony. So if you look at Graph 16, for example, it requires a trusted setup. And the powers of Tau ceremony enables you to do that using MPC. So you can do that directly with the Zokrates CLI. And also in Zokrates.js, actually. We also have support for log statements that you can, where you can inspect certain values of your code at runtime. We have support for the Marlin proof system that I mentioned earlier, which is a universal setup, which means that you can do one setup and then use it for different circuits. We also changed a lot of the syntax following some feedback from members of the community. And finally, yeah, this playground, which is now accessible, which I invite you to check out. OK, I think that's all I had to share. So thanks for listening. If there's any questions, yeah, I'm happy to take questions.
Hi. OK, yeah. Can we use the new Nova support to write another but shorter ZK EVM?
That's a good question. I think in theory, yes. I'm not sure it would be the most efficient. But there were already, actually a long time ago, VMs that were built on top of recursive snarks, but they were using recursion at each cycle of the CPU, which was quite inefficient. But maybe there's a new take that could be that you can have on that.
So that would be one cycle for each opcode, or?
That was the case in those project 10 years ago. It's a project called TinyRAM, where that's what they did. They basically took the state of the CPU and just ran each time one opcode, and then have a recursive snark each time. Yeah. But maybe there's other approaches to leverage this proof system.
Cool, thank you.
So instead of making users to write very optimized code, have you put effort on kind of making the compiler kind of figure out what the user wants and then optimize the circuit based on that?
So are you saying that, OK, is your question that we should, instead of having low-level code, have the compiler detect when it can do those optimizations, right?
I mean both, but like you were only talking about the other case.
Right. So this is something that, as I mentioned, this is something that we do currently, where we identify some of those use cases, some of those cases, and just have them in the compiler. But it's just really hard to cover them all because it's really use case dependent. Here, this is just for one part of the SHA-256 function, but there's so many different things that you could optimize. So I think it's actually a good idea to open that to developers, but in a way that's quite separated from the rest of the high-level code.
Any other questions, anybody?
Thank you.
Hey, no more questions? Then thank you, Thibaut. I was made aware of a little mistake that I made. So the happy hour tonight is from 6 p.m. to 8 p.m., not 8 a.m. It's not going the entire night. I'm sorry, guys. But still worth checking out the first floor after our last talk. And I am also certain that there will be some other cool things actually happening on the second floor as the program of Devcon After Dark. This is the one thing that I didn't tell you about in the other break. So as the last thing that we're also doing as continuous Devcon is allowing community meetups, gatherings, initiatives, activities to happen in the evenings in the venue. That is anything from a chess tournament to, I think currently in the hacker basement we have an evening in the dark forest. Tomorrow we will have autonomous worlds in the hacker basement. Tonight Bert just tweeted me that we will have a demo session with Villian about Otterscan, Aragon, Sourcify in the workshop room 1. So it is definitely worth checking out this Google Sheet, the public link that's also linked in the app and everywhere to check out what things are going on the community side of things after the actual program. But without further ado, I'd like to introduce our last speaker of the day. It's Chi Cheng, and he is in the PhD team of the EF, and he likes building privacy or scaling related applications. And today he will share little things he has learned in developing Halo 2 circuits. So big applause and a round of welcome to him.
Thank you. Hello, thank you for coming. I'm CC from PSC. Today I'm sharing some of my developer experience from programming the circuits, ZK circuits. So we know in ZK snark, well, we allow the prover and the verifier, they agreed on the algorithm. And then prover can provide a proof input and the output to the verifier. And then verifier can be convinced that the computation, the output is correct corresponding to the input without recomputing the algorithm again. So lots of scaling and privacy we are getting from this snarks. And I'm going to unroll this process more. It's not a full story, but you as a circuit developer, you are on the left-hand side. You define some constraints, and then you send a verifying key and proving key generated from these constraints and send it to a verifier and approver. We call this setup time. This is like when you finish the circuit development and deploy the project and setup is ready. But at a proving time, like whenever you need to send a proof, so prover would run the computation and get the computation traces and fill in to the circuits, and using the proving key to generate a proof and then send the proof to the verifier. Today we don't care about like how sausage is made. Like we care about like how do you turn the computation into circuits. Okay, so if you're coming from like a normal programming world, for example, if you write Python, C, Rust, anything, your brain works with function, loops, and if-else, this kind of good stuff. But when you enter the circuit world, you need to do the arithmetization, and you need to get the circuit trace. So you're thinking in the computation trace of the whole computation, and you just think to verifying these computations with math and equations. So it's like that. So before we going to introduce some tricks and development tips, let's talk about the rules of the game, like how does circuit thing work. So first of all, like all computation is represented in finite field arithmetics. So a finite field element is, you can think it as an integer, and it's a positive integer and less than a number p. And let's say if p equals to 3, then if you have two field elements, 2 and 2, you're adding together, you actually got a result of 1 because we need to do it in modulo 3, modulo p. And p is usually a very large number. For example, it's 254 bits. So the takeaway is that we need to represent like your computation in field numbers instead of bits and bytes, and you need to watch out for the wrap over and overflow stuff. And then we get this grid of stuff, like a paper. You can fill in the field numbers inside those cells. And if you can expand this grid with more columns, but like for every new columns you added, it would be more costly. But the rows are basically free, but they are kept up to some limit. Let's say 2 to the 18, like this is 260K roughly. So ideally you want to use as much row as possible until like maybe you have more computation you need to do. Then you add more columns and add proving costs, proving times, verifying costs, something like that. And we have to distinguish some types of columns. These columns are distinguished by like who can see what and when they are like when values are assigned. So we have the pink one is the advice column. It is only visible to prover. It is determined at the proving time. The prover witness the value inside this column. And we have a fixed column. Fixed column is assigned at a setup time. So both prover and the verifier have a copy. And then the instance column. So this is the value is visible to verifier. So we can the prover can fill in the input, then the output in a proving time. So so that we can have the scenario in the first slide that the prover witness some private values and then some public instance values for the input and the output using the proving key to generate a proof. And then verifier can verifying the proof and also take the 10 and 100 layer. You can verify in the contract or do other verification if you may. Right. Okay, so now we have the grid, we have the columns. We need to define like what values in the cells are correct or valid, like what values are allowed to put in the cells. So these are constraints, and I'm going to introduce two types of constraints in Halo 2. The first one is the custom gates. So this defines the constraint in polynomials. So the gate looks like this. We have we choose the cells from column A, cells from column B, and cells from column C. You can choose whatever column you want, and you can choose the relative position. For example, I want the next column of the in relative to the A cell, and then you can define the you can define a polynomial to constrain like okay, A must equal to the B plus B the next cell of the B, and then but like this gate will be applied to all rows in the column. So sometimes we don't want to do that. So that's why we have a selector here. So this selector will be the 1 or 0 value. So if this selector is 1, then the whole then this expression here must equal to 0. Then our constraint is enforced. But if selector is 0, then the whole expression is already 0. So this constraint does not necessarily hold for that particular row. I just want to quote the sentence from Vitalik I heard from his talk. He said, like, everything's a polynomial, I'm a polynomial. So to give an example, I borrowed an example from Intel's Fibonacci circuit example. And we want to prove the nth term of the Fibonacci number. And then we can fill in the value of 1, 1, 2, 3 by everything into the grid. And we define the gates that left plus right must equal to the sum. That means like left plus right minus sum equals to 0. And we use the selector QFib to determine like which row we want to enforce this constraint. So here is one way to do it. Like we make this gate looks like very straight. They are on the same rows. But you can see that we are using 3 columns here. So this is the other way you can do it. You can make it like the sum. You can fold it to the next cell, and it uses less columns, but it works the same way. It still can give you your desired computation result. So it's flexible. You can determine the shape of the gates depends on your problem to solve. And the second tool to constrain the grid value is copy constraints. So I have this yellow tab here to glue the values of 2 cells together. And if they are glued, so the value assigned in the cells must equal. And this is determined, the glue must be determined at a setup time. There is no way you can change it at a proving time. But it's very cheap and use it as much as possible. So the final rule is that the prover can be evil. Like, I like to think prover or like everything with a verb, prover, verifier, miners, things like that, as a cyborg. They are the human who runs the machine, and like machine runs the algorithm, but like human are attracted by incentives, and they could do all kinds of stuff. So if you didn't write your circuit right, prover can witness the wrong values and still convince the verifier to do stuff. So if you are like designing a decentralized mixer for this, and prover witness some value, they can like withdraw the money out of the air, then your project is hacked. Okay, so let's get into tricks. Okay, let's start from the simple one. How do we limiting the options in one cell? For example, I want this cell to allow only values 1 or 2 or 3, nothing else. So to do this, we can define a gate that has this expression, the cell value -1 times cell value -2 times cell value -3 equals to 0. If you plug in the 3 into the cell, this expression will be 0. But if you plug in this 100, then this expression would be like 99 times 98 times 97. It won't be 0, so this constraint is not satisfied. If you witness 0, this would not satisfy either. Okay, next let's converting if and else. So for example, we have this sample program here. We have input A, input B, and there are like few elements, and happy is like a Boolean value. And if happy, then we do A plus B. If we are not happy, we do A times B. And then, so for example, we could have a circuit that looks like this. I use the glue to glue the public instance value to the private value. Like in the left one, we can see that we witness A as 5 and B as 6, and happy as 1. So we are doing the addition path. So we got the value 11. And the second one, we still have the same AB value, but happy is 0, and the desired output is 30. We just gave an example here. We haven't constrained them. So the way you turn this if else into the gate expression would be happy times A plus B plus 1 minus happy
times A multiplied B minus output equals to 0. So that if your happy is 1, then this expression will be enabled, and this expression will be disabled. The other way is same. If the happy is 0, then this expression is enabled, and this expression is disabled. So let's see. We have like example value witness in here. These are all satisfied, but like we kind of forget something here. Like prover can witness 3 here and still got the 3 times 5 plus 6 and like get the output minus 27 equals to 0. So what's wrong here? It's because that every input is a finite field element, but if we want Boolean value here, we need another constraint to make it Boolean. So we need this additional constraint here to limit the happy to be 1 or 0. So using the tricks before. Okay, next we need to convert the loops into the circuit. And let's start with an easy one. This function initiates a variable r as 0, and then it runs the loop 5 times and add 5 to r and do it 5 times. And like 5, these are our constants. So it will be easy to lay out like the value of r started with 0, and the next plus 5, plus 5, plus 5, all the way to the output. And then we constrain the value 0 to 0, 25 to the output to the output. So we will have this gate expression like this. Easy. But what about this? This looks like exactly the same loop, except like how many times of loop is determined by the prover input n here. So this will be a lot trickier because you might have we can imagine a computation trace looks like this. First, prover inputs the n here, and the output 25 here, and or input 3 here, and input here. And notice that this algorithm, this is basically the very inefficient way to do 5 times n. And also note that this n could be like arbitrarily large, but like we don't have an arbitrarily large circuit. So like we cannot do infinite loops. We can only do like only up to a certain amount of computation. So we need to like restrict this, how big this n could be. Let's say we restrict it to 5. And then we need another check to make sure that n is actually less than 5, but it's out of scope of this talk. And we want to focus on how like to determine the computation of R inside. So yeah, let's first do the copy gate for 0 to 0 and the output to output. But because the copy gate output can only locate it at the same place of the cell, so if the n is 3, we need to like repeat the result here. All right. One attempt is to solve this is we add a prover witness selector here. So let's put 1, 1, 1 here when we are still in a range of n. and then 0, 0, 0 here to do the repeat. And using the if-else trick we learned before, we can define this gate expression. But then, how do you prevent like the prover doing this? So like if prover like they don't follow the rules, they witness 0 and like 1, and then go back to 0 and 1. And if you do the math, you can realize that prover can witness 3 and like output to be 10. Then it convinces you that 5 times 3 is 10. Then yeah, it's a failure. That people say it's like blockchain is all about trust. I would say blockchain is all about trust issues. And so let's observe like different cases of n. Like n is 0, n is 3, n is 5, and we observe that s can only like for the valid case that you can start with 0, but once you are 0, you can only go with 0 of the rest of the row. You can start with 1, and you can turn 1 to 0 anytime, but like once you turn to 0, there is no way to turn back. So we can identify the state transition like this. So this is a trick Han taught me. So you, when you start, you can start at a 8 state. That means we need to add 5. And you can, from 8 state, you can go back to 8 state. You can go to the past state, which is a 0, and the R remains the same. But the point here is that once you enter the past state, there's no way to go back to the S state. So we can define the constraint here. And the only thing we need is here. Like if the current cell S is 0, for example here, then the next cell must be 0. So this constraint can help you achieve that. And also we need to make sure the selector is binary. Now we have the final touch, like to make the input, accumulate this input value and copy back to input. This still follows the same rules from the prover witness selector. So, like, why are we doing all these tricks? Why we need to like doing this repeating and like state transition thing? Because like in CPU, we take instruction one at a time, and if you have an if-else branch, and if the branch you didn't enter, that just you can forget it and you don't compute it. But for a circuit, you need to flatten all the computation. All paths you need to include it in your circuit. And then so you can see here, even though we only witness input 3 here, and these 3 rows, we still need them and like witness some dummy values there. Because we need to consider the case that prover could witness 5 here and like use all these spaces. So the takeaway here is that the challenge for the circuit developer is that we are working with the computation trace instead of the execution itself. So we need to flatten the path and like work all possible paths of your computation. The second is that because we are working with field element instead of bits and bytes, so we need to do some math and equations there. And the third is that we need to work with the verification mindset, because prover could be witness malicious values inside your circuits. And the tricks we talked about here are like using the Boolean value and one time times the true path and the other times the false path. This can convert the if-else statement into the circuit expression. And for the complicated loops, you need to identify the state transition of the your program logic, and then design constraints for them. Yeah, that's my talk. Thank you. Thank you for listening. Thank you. Do I have time?
I think we have time for a couple of questions. Yeah, the mic is coming.
Hi. I thought that in the original Blanc, the copy constraints were pretty expensive. Can you expand why that's not the case in Halo 2?
Sorry, can you say?
I thought that in Blanc,
yeah,
the copy constraints were expensive. Can you expand on why they're cheap in Halo 2?
I think they are. I think they are the same. I think that they are cheap in terms of when you use once and like you use it a million times, they are the same cost. So I think yeah, that's the idea.
Okay, thank you.
You're welcome.
Any other questions?
Great presentation. For somebody that wants to learn more about CK proofs, what path do you recommend to go? Right now, I think the circuit explanation is really good, but I got lost in some bits. So what would you recommend me to read in order to follow you better?
So it's a question that what kind of material I recommend to read? Okay, thanks. Like there are too many. I don't have a good one, but like I would recommend try to find a simple circuit project and try to run it, try to tweak it, like removing something, and try to start it. I think that would be the good way to learn how circuit works.
Thank you.
Thank you.
You mentioned like in the, here in takeaway points that you have to prevent the prover from cheating. How often do you see when you're writing the circuits how often do you find bugs because your circuit was under constraint and the prover can cheat?
Oh, good question. So the question is that like how do we find if there are bugs in the?
Or how often does it happen that you find a bug because it's under constraint and the prover can cheat? Or because the constraints, if the constraints are wrong, if the gates are wrong, or just trying to compare it to like usual software development, when you just basically write the logic wrong, right? How often do you see that the gates that you come up with are doing the wrong thing?
So when we are developing the circuit, oftentimes we'll like realize, oh, we forget this constraint, and like prover could witness that bad values. Like we found a lot of bugs in like development stage, but like once you want to go to production, like we would like do some external audits and like try to find as much bugs as possible. And like when you really enter the production, like you can only like cross your fingers but like I heard Vitalik has an idea that says they can use like 2 provers for the rollups, and like if they can witness, like they can create a valid proof or 2 different outputs, then you can like stop the rollup or stop your application, and then do the fix. Yeah.
I see. Thank you.
Thank you.
We have time for another question. Anybody else has one? You got good questions.
So yeah, sorry for hijacking the questions. Just let me know and I'll stop. So when you write the Halo 2 circuits, you're writing using the Rust lib, right? Do you think that adds a lot of overhead compared to if you were using a DSL like Circom or Zokrates, for example?
I definitely feel like Circom or like DSL are more readable, more auditable. But the thing is, when you don't have DSL, you just have to
So you would like to have a DSL for Halo 2?
I like what?
Would you like to have a DSL for Halo 2?
Yeah. That would be desired and great to have a DSL for Halo 2. Yeah.
I thought someone released one some months ago, didn't they? Or maybe I dreamed that, but
I don't know. Anyone up here know?
I think it was someone from Darkfight that posted on the ZK podcast Telegram group.
Oh, it sounds
but
great.
Maybe I also dreamed that. I don't know. But yeah, thank you.
Yeah. I'll go check it out. Thanks. Thanks for the info.
We're also out of time. So.
Okay. More questions? If not, thank you, Cici.
Thank you.
And this concludes the program of the Cold First stage today. Thank you all for coming. If you didn't get enough yet, you can still hang around in the second, first, and basement. Second and first floor and basement. We will be closing the upper floors soon-ish. So if you want to network, hang around, or whatever, make your way to the second floor or lower. And yeah, thanks all for coming. See you tomorrow again, and have a great evening.